Hi, I'm Susan. I'm really excited to be working with our team at Duke to introduce this course on the foundations of computer programming with JavaScript, HTML, and CSS. We've designed this course for beginners with no previous experience in programming who want to begin to explore a career in programming. In this course, you will begin to learn how to think like a programmer, analyzing problems, designing solutions called algorithms, and translating your algorithms into programs. Using HTML, CSS, and JavaScript, you will be able to see your programs in action by building interactive web pages, a useful skill to have whether you decide to go further in programming or use these web development languages in other fields.
Hi, I'm Robert, and I hope you'll enjoy the interesting projects we've made for you to complete in this course. In week 1, you will learn to create your own web page using HTML, the language that defines the structure of your web page, as well as CSS, the language that lets you change the appearance of your web page easily. Next, in week 2, we'll tackle the green screen problem, where I and Drew, who you'll meet next, will launch into outer space with dinosaurs. To do this, we will learn some important programming concepts with JavaScript, with a focus on manipulating images using special JavaScript libraries we've designed. The programming concepts and skills you will gain will serve you well as a programmer, whether you're working with JavaScript or any other programming language. In the third week, we will bring together our HTML, CSS, and JavaScript skills together to make your web pages interactive. By the end of this course, you will have designed a web page that allows users to upload their image files and apply image filters that you created.
Hi, I'm Drew. One of the most important concepts you will learn is how to solve programming problems. This will build the foundation for you to understand what computer scientists do and think about as they write programs. Knowledge that will be useful to you whether you continue on to learn more programming yourself or need to collaborate with computer scientists to create programs together. The skills you will learn are applicable to any programming language, not just JavaScript. While the syntax may be a bit different for other languages you will learn, the same fundamental principles apply.
Hi, I'm Owen. After finishing this course, you'll be ready to make web pages and to program in JavaScript as well as other languages. If you decide to continue in our specialization on Java programming, you'll use the programming foundations from this course to learn how to solve problems and write code with Java. In addition, the web development skills you'll learn in this course will come in handy in our capstone project, where you'll learn to create a web page to host a recommendation system that you build and develop, similar to how Amazon or Netflix recommends books or movies based on a user's preferences. Now that you know what this course is about, let's get started.
I'm here with Elise Murphy, who finished her undergraduate degree at Duke last spring, did an internship at IBM this past summer, and is going to be a master's student at Duke this fall. So Elise, you've been programming since high school. Why don't you tell us a bit about how you got into programming?
Sure. I actually took my first class, AP Computer Science AB, the last year it was available, in my sophomore year of high school. My mom was actually a computer science major in college, and my dad was a stats major. They own a website company, so they told all of my sisters and I, at least give computer science a try. It's definitely worth knowing even just the basics of Java. And if you like it, you can pursue it. If you don't have to, but it's good to know. And after my first class, I was hooked, and it's been history ever since.
So what got you hooked on computer science in your first class?
I think when the first time that I was looking at it, it just seemed like everything I was exposed to was just so over my head almost. It was just like, I remember thinking to myself, anyone who understands this, anyone who can explain this like it's easy is a genius. And then I had my first moment of just getting it, and I knew that I was one of those people. So every time I have one of those aha moments, then I remember how exciting it is to get a program running right.
So to wrap up, we have lots of people out here from a variety of different backgrounds. Do you have any words of advice or wisdom for them as they delve into the field of computing?
Yeah, I guess the biggest point I would have is just that a lot of people think of computer science as something that only a computer scientist needs to know, or someone who's going to have a hard coding job. But honestly, computer science is in every field and can benefit really anyone that takes it and knows about it. So, which is probably the coolest thing about it. You know, it really is in every field and advancing every subject. So anyone can benefit from learning computer science.
Okay, great, thanks.
Hi, I'm Elizabeth. I'm part of the instructor team here at Duke University. Before you get started with this course, I want to make sure you're aware of some important resources and give you some tips for doing well. In this course, you'll see readings labeled Try It and Programming Exercise. Try It readings encourage you to try things you've seen in the videos yourself so that you can get more practice writing code. Programming exercises contain instructions to help you write your own programs. There are also quizzes so that you can make sure you understand everything from the videos and check that your code works properly. I also want to show you the course site, dukelearntoprogram.com. You can see we have a page for each course and a page of frequently asked questions about the specialization. This has everything from certificates to the software we use in the course. If you go back to the home page and select the course you're working on, you'll get to that course's main page. First, let's look at the Duke JavaScript environment. You'll learn all about its features later in the course. For now, just remember that you can get to it on the Course 1 Duke Learn to Program website. Project Resources contains examples from the videos, so you can look at that code in more detail or experiment with it. Documentation has a summary of the HTML, CSS, and JavaScript you'll learn in this course. This is useful if you want to review the syntax of an HTML element or see what JavaScript methods you can use, for example. This isn't the full documentation for all of HTML, CSS, and JavaScript, but it's a useful reference for this course. Last, we have the Frequently Asked Questions, or FAQ page. The first thing you should do when you have a question about an assignment or a quiz is check the FAQ page to see if we already have an answer for you. This page has questions about Course 1, since we're in the Course 1 part of the site. For questions about the specialization as a whole, there's a link up here back to the general FAQ page that you saw earlier. So hopefully this video has given you an idea of how the course is structured and what resources you'll need to know about. If you have any feedback about how we can make these resources more useful to you, please let us know in the discussion forums on Coursera. To help you do your best, we want to give you some suggestions about how to learn in the course. First, do a little each day. It's really hard to learn programming all at once. If you do a few course items each day instead of trying to do it all in a day or two, you'll remember things better, you'll be more motivated, and you'll have more time to work through problems in your code. Speaking of problems with code, also known as bugs, it's normal to make mistakes when you're programming. So our next tip is, don't give up. Everyone gets bugs in their programs, and part of programming is figuring out what's wrong and how to fix it. When you're programming, we really recommend following the 7-step process. This means you should plan how to solve the problem before you start writing any code. The 7-step process is important because it gives you a method for solving problems. Then when you've figured out a solution, you can start writing code. Once you're ready to start writing your programs, make sure you've read the relevant documentation so you know what Java methods exist and how to use them. Refer back to the documentation as often as you need to. Next, take advantage of the live coding videos and the practice quizzes. For the live coding videos, this is a great opportunity to program alongside the instructors. Finally, for the practice quizzes, even though they don't contribute to your final grade, there's still a good chance for you to test your code. Use the practice quizzes to find and fix problems before you move on to the graded quizzes. Finally, if you're still having trouble with your programs, ask for help from the instructor team and your peers in the course discussion forums. Part of being a good programmer is knowing how to ask for help effectively. We'll talk more about that in the next video. It's completely normal to struggle with learning programming, and when that happens, the instructor team and your peers in the courses are here to help. The best way to ask for help is through the discussion forums, which you can find here. You can also answer questions in the discussion forums, and we really encourage that, because explaining programming concepts is a great way for you to learn, and you also get to help out one of your classmates. Here are some general tips about asking questions in the forums. First, Before you start a new topic, you should check the FAQ pages on DukeLearnToProgram.com and existing forum threads to see if your question has already been answered there. The first thing you should do when you have a question about a programming assignment or a quiz is check the FAQ page for that course. Second, start a new thread if you have a new question. Don't post your question as a reply to an existing thread unless it's really closely related. This way it's easier for people to see what your question is about and help you more quickly. Third, if you need to post code, use the code formatting box, which is the one with this symbol on. This is much easier to read than if you just copy and paste it directly into the post. We also want to give you some tips on writing a good question so that others can help you most easily. If you're having trouble with a programming assignment, name and link to the assignment you're working on. If your program is throwing an exception, you can post a screenshot of the error message and also the line of code that it occurs at. If your program is producing a result that's different from what you expected, make sure you say what input you're running your code on, the output you expected to get, and the output you actually got. For example, suppose I'm trying to write a program to change every green pixel in an image to blue. I should share the image I'm running my program on, my input. I should explain that I'm expecting every green pixel to become blue, my expected output, and I should also explain that every green pixel is actually becoming red, my actual output. Then others in the forum can better understand the problem I'm having. If you have to share some code because others can't help based on the description of what your program is doing, it's okay to share a few lines of code, but don't share your whole program. Figure out which part of your program you think the error is in, and share a few lines of that method. Don't copy and paste your whole program into your post. If you have a general programming question, such as how do I write a for loop, or how do I add items to a list, it's okay to post those lines of code because they're so general. Finally, if you have a conceptual question, make sure you name and link to any course materials you refer to. When you're answering questions, it's okay to share code for general programming concepts, such as how do I write a for loop. However, if someone is having a problem in their code, don't give them the solution. Try to guide them towards fixing their code themselves by giving hints. If you don't know what the problem is, suggest what they might do next to debug their code. Let's look at some example posts. In this post, I didn't really ask for help very well. I said my code wasn't working, and I asked if anyone knew what might be wrong, but I didn't really explain what the code is trying to do, what it's actually doing, or what troubleshooting I had tried so far. I also posted a lot of code. So I edited my post, and now it's much better. You can see that I explained which assignment I'm working on, and I provided a link to it. I also explained what happens when I run my program, so my actual output, and what should have happened when I run it, so my expected output. Finally, I only posted a few lines of code that I thought the problem was in. Now that you've learned how to ask and answer questions about your code, you're ready to start learning how to program. I hope you enjoy the course, and I look forward to interacting with you all in the forums. Good luck!
Welcome back. Hopefully you're excited to start learning how to create your own web page in HTML. Before we dive into those details, we're going to learn about a tool that you can use to do this. This will let you follow along with the examples as we go through things, and of course explore and create as you want. You can play around and make your own web pages, trying out the concepts that you learn. There are many possible tools that we could use to make web pages, and we're going to use one called CodePen.io. Let's see how you can use this tool. I've gone in my browser to CodePen.io, which is the tool that you'll be using to create a web page. On this first page, you can see links to other people's pens, which is what they call projects, and you could go explore them if you wanted. What we're going to do is go up to the top and click New Pen, which lets you make your own project so that you can make your own web page. By default, there are 3 frames at the top. We're going to close the one on the right because we're not going to need that one, which leaves you with one to make HTML and one to make CSS. You're going to learn about HTML shortly and CSS later. If you were to write HTML in this top frame, and you don't have to worry about the fact you haven't learned that yet, you'll learn it very soon, you would see as I type it, it shows up in the bottom formatted as it would on an actual web page. Now, as you learn later about CSS, you'll be able to use it in this box on the right to change the style and formatting of your web page as you create it. So here I changed these list items from black text to blue text. Of course, this web page is not very interesting. You can make much more sophisticated web pages, as you'll learn to do shortly, which have images and more complicated formatting. Here's one which has a lot of HTML as well as a lot of CSS. And by the end of these next couple modules, you'll be able to do this to design web pages as you want to. Now that you've seen CodePen.io, you know how you can create web pages once you know HTML. Now we're ready to dive in and learn HTML so you can express anything you want in a web page.
Today you're going to start learning about web pages and the language and concepts for creating your own web pages. One of the amazing things you can do on the internet and the web is create things like web pages so that billions of people, anyone with an internet and web connection, can see them. Let's get started in understanding and mastering the concepts and language, the nuts and bolts of making a web page, so you can make your own web page. You probably are quite familiar with web pages. You've seen and navigated them. For example, you may have looked at Wikipedia web pages. You've seen that some web pages are easier to read than others. Some are full of really fun and interesting links, words, images, videos, and more. Here is a Wikipedia web page that describes web pages. In the web page is an image of a web page. So we're talking about a web page with a picture of a web page, and in that web page is information, excitement. You'll learn about the basics in creating web pages. Your own imagination and creativity will help you apply this knowledge in creating your own pages. For example, there is bold or emphasized text on the web page. You'll learn about how to make some parts of a web page be more forceful than others. There are links to other web pages on this web page. Links are what helped transform how people use the internet and the web, linking from one page to another so that you can learn amazing things by following links. This web page has images. You can also put videos and audios on a web page, but we'll be looking at images first since they're very simple to access and use. To access a particular web page such as this one, you need the address of the web page. The address isn't part of the web page. It's used to access the web page online. Once you share the address, anyone in the world can access your web page. In this course, you'll be creating web pages that you can share with anyone in the world. The address is called a URL, or Uniform Resource Locator. In order to write web pages, you're going to learn hypertext markup language. This is the language used to create web pages. Most people use HTML as an abbreviation for hypertext markup language. It's much easier to say, and it's easy to use when searching for information online. Note that in learning HTML, you are not learning a programming language, but rather a markup language. HTML does not run on a computer like a programming language, but is used by web browsers to display a web page. You may have written documents in which you select text and make it bold, or underlined, or italics. This is a way of marking up the text to display in certain ways. HTML uses structural marker called tags that the web browser uses to display the web page. When you write HTML, you get to describe what you want to appear in the web page you're creating. The browser uses HTML to render the web page so that it's viewable on a computer or on a phone or somewhere else a browser runs. Because HTML is a markup language, that description includes not just the text and images, but markup describing the formatting you want. For example, bold text like you just saw, tables like you will see in the next lesson, or a variety of others ways to display your information. You'll use HTML to specify meaning, like bold or link, but you won't use HTML to specify how to display bold text, like what color to use. For that, you'll use another language, one you'll also study a little later. There are different ways to display items. You will later learn about CSS to provide ways to enhance the display of your web page. You may specify that you want to emphasize some text, but how exactly do you display emphasized text? CSS lets you describe that. Maybe it's italics, maybe it's bold, maybe it's huge and red. You'll learn CSS in a later lesson. In order for different browsers to interpret HTML on web pages, there must be standards. HTML5 is the current version of HTML. It's a collaborative standard, many people working around the world to decide on the standards. The first standard for HTML was in 1993. Wow, that was over 20 years ago. That was a very different time. Most people used very slow modems to connect to the internet then. Web pages were much simpler then, and images were slow to load. Today we have images, video, audio, and more, but we still have an HTML standard, just one that's up to date with current capabilities of the internet and the web. The most recent standard for HTML was in 2014, and it has evolved with the changing times. HTML5 has features to support multimedia that would have been unimaginable in 1993. Here's an example of HTML for a web page, and that web page displayed. You'll see that the HTML markup has many tags. Each tag is set off by angle brackets from what's between the tags. We'll look at the tags used on this page, but you can also see that the displayed web page does not show the tags. It shows the phrase "Hello World," and you can read the title of the web page in the Browser tab. The title is Hello World Page. First, you see the HTML tag to indicate we are using HTML to define the components of a web page. The web page is defined between the starting HTML tag and the ending HTML tag. All valid web pages using HTML contain these tags. As we'll see, there's a start tag and an end tag. The tags match up, but the end tag has a slash that indicates it's the end tag. Next, you see all the header information defined between the start and ending head tag. Again, the end tag is /head and the matching start tag is head. Next, you see the title tag. Note that all the content between the starting and ending title tag is displayed as the title of the web page. Hello World Page. Next, you see highlighted the body tags of the page. Whatever content you put between the start and ending body tags will be displayed as the body of the web page. Finally, we see a short paragraph within the starting and ending p tags, and you can see that content. Hello World is displayed in the web page. We'll see this HTML often. What's between the body tags is what the user looking at the web page sees.
Let's look more closely at some different types of HTML tags or elements. Right now, we will look at two types of elements. One group is metadata elements. These contain information about the page. Examples include the HTML tag, head, and title tags. Sectioning elements, which define regions of the page, include tags like body, header tags, and div. In the context of a web page, metadata is a set of data that describes and gives information about the web page. The HTML tag is a metadata element. All other elements must be defined between the HTML start and ending tags. HTML tells a browser that it should use the HTML standard in displaying the web page. The head tag is also a metadata element. It contains general information about the page. This includes the title, information about scripts, and information about displaying the page using CSS. The title tag is a metadata element too. It specifies the text that is the title for the page and must be nested between the start and ending head tags. For an example here is the beginning of the HTML from DukeLearnToProgram.com. The HTML tag, the head tags between which other metadata goes, such as the title tags. Next, we see examples of sectioning elements. The body tag is a sectioning element. The start and ending body tags define the body of the whole web page. All the text and other items seen on the page will be inside the body tags. Other sectioning elements define sectioning within the body of the web page. For example, the H1 tag defines a region with a more important and usually larger header. The H in H1 means section head. The H2 tag is also a section header, but typically a little smaller than an H1 tag. The smallest header tag is H6. The div tag is also a sectioning tag. This tag defines a section or division of a web page. It is useful for grouping elements together to use CSS styling. Sectioning elements can also be found in the HTML for DukeLearnToProgram.com. The body starts here after the metadata, and the closing body tag is not shown because there's a lot of HTML on this page. Here is an H1 header element. Here is the first div on the page. It uses the CSS class title bar. Hopefully, the layout of a web page's HTML makes more sense now.
We'll see here how some simple style tags change the appearance of text on a page. Here's an example using the bold tag. The B tag typically makes text bold or standing out from other text. Notice that there is both a start and end B tag. Here's another example of bold. As we'll see later, the bold text might be displayed differently if you have trouble seeing. For example, if the web page is used by a screen reader, that's a semantics or meaning and helps the screen reader change how text is read to a blind user, for example. Here's an example using the emphasize tag. And here is an example nesting different tags. Let's see how all of this would be displayed on a web page. Notice that some of the words are bold and some of the words are emphasized in a slanted text. These two lines are displayed in bold text. And this line is displayed using a slanted text. Look what happens when you nest tags. Here we have the bold tag nested inside the emphasize tag. The outermost tag is the emphasize tag, and the innermost tag is bold. The innermost tag applies to the words example of nested, and the rest of the words inside emphasize get emphasized with slanted text. You may be used to editing a Word document where you type text. What you see is what you get. But with markup language, what you see isn't what you get. The HTML you write will be displayed in a nicer way, the way you specify it to be displayed. You can put images, video, and audio on your web page. For example, here we have a picture of Hillary Clinton welcoming Sonia Gandhi. Different types of media have different tags, but we will show you how to use images since they are the most straightforward. Anytime you want to put an image on your web page, you use the image tag. Here is an example of an image tag to display a picture. And here is another example. The two of them look slightly different, and both have syntax that we've not seen before. Inside the angle brackets for the image tags, we have options, which give extra information about what we're doing. In the example of an image tag, we need to specify what image to display. In fact, even though they are called options, and thus sound optional, some options are required. For example, we have to specify what image we want to display, so that option is required. Notice there is not a separate end tag. An image tag specifies the actual image location in the tag, so it doesn't need an end tag. It has the slash in this tag to indicate an additional end tag is not needed. As we just said, you must specify what image you want. So the source or SRC option is required. It specifies the web address to the image to load. Width is an optional tag. It can be used to reduce the size of the image displayed. Otherwise, the original size of the image is displayed, which could be quite large. There are other options you could specify, but we will see better ways to process images when we get to CSS. Here we display HTML that illustrates how to link to another web page, and below we show how this HTML is displayed in a browser. The anchor tag, or A tag, is used to specify a link to another website. The href attribute specifies the URL for that web page and is required. You must specify some text between the start and end anchor tag. This text will be clickable to take you to other websites. Now, making a web page look really good isn't easy. Designers can make elegant web pages because they understand HTML really well. Designers understand how to use the tools to get those fancy web pages. Now you are learning the basics of HTML so you can get started on creating simple web pages. You're learning a foundation that you can build on. Notice that web pages can be displayed on different types of devices. Your laptop, your phone. It's a bit more of a challenge to create a web page that displays well on both large and small displays. Having interaction with a web page, such as ordering a book from Amazon's web page, is even more complex. For now, let's get started with just the basics so you can create a web page.
In this lesson, we're going to talk about a few concerns or issues that you may face when using images or photos in the web pages you create. We've made web pages we've shared with you, and you've made web pages that use the IMG tag to show a picture, image, or photo on the web page you create. In this course, you've used the website or web tool CodePen.io to create the images. But it's possible you may have already used other tools or sites like WordPress to create images. Whatever tool or site you use, you'll need to find images that you can use in the websites you create. A URL that is the source for the IMG tag you use in your website. In some cases, there may be concerns with the person, organization, or group that created the photo you display on a web page you create. The creator has certain rights, called copyrights, and you'll want to respect these. In some cases, there may be storage concerns. Where are the images stored that you've included on your web page, and who pays for that storage? You may want to store your own images so you can link to them in web pages you create. There are similar concerns with videos, though videos hosted on YouTube are very easy to include in the web pages you create. We'll briefly talk about usage rights for images or photos you find online. We'll give you a very basic understanding and urge you to explore more on your own. Some images and photos are copyrighted. This means specific rights are held by the person or organization that created the images. You should respect these rights, thinking about rights you'd like to have for images you create. Copyright laws are different and vary from one country to another. You should likely have a basic understanding of copyright in your own country if you're going to make web pages that might have a commercial value. Typically, if you're making a web page for personal use, like the pages you create for this course, you don't need to be concerned with copyright laws. However, you do want to understand the usage rights and know that for images that are copyrighted, there are some rights. Many images are in the public domain and are not copyrighted. The flag from Brazil that has been displayed on this page is in the public domain in the United States, in Brazil, and in many other countries. Images in the public domain have no rights associated with them, and you can use them freely. Many images can be found using Google Image Search, and you can fine-tune the search to specify that you want images that can be reused. The Wikimedia Commons is a website and storage area where images that are more free to use can be found. Some of these images have what are called Creative Commons licenses, which specify how you can use the images. Once again, for your own personal web pages, you typically don't need to be concerned with these rights, but it's still a good idea to have a basic understanding of image rights. Some Creative Commons images are not copyrighted. Some have usage rights that allow you to reuse them for non-commercial purposes. The logo on the right specifies non-commercial use in the European Union or EU. Other licenses require that you license your own work in a similar way. These are called share-alike licenses. The logo on the left represents such a license. In this course, we try to use images that are in the public domain. In addition to usage rights, using images on web pages you create may have image storage and hosting concerns. For example, suppose you want to include an image of the Chinese flag on a web page you create. You may use Google Image Search to find a URL that you can use with the source argument of an IMG tag, and you may take steps to ensure that the image of the flag you find is in the public domain, so there are no usage rights concerns. The URL shown here is for just such an image. You've done great. You've properly concerned about usage rights, and you've created a really nice web page. But suppose 1 million people view your web page. That means the flag image is seen by 1 million people. It also means that the flag image is sent from the website which stores it across the internet to 1 million users that might be scattered all over the world. Someone pays for hosting the image and for serving it to everyone, even if it's not you. This could be a concern that you need to understand. When you use a URL in a web page you create as part of an IMG tag, you've included what's called an inline link from your page to another web page. Inline linking is also called hot linking and means that the image is stored on another site, but visually appears in the site you create. Typically, you don't need to worry about copyright and usage concerns for your own personal pages. However, if you create a web page with lots of views or lots of traffic, there may be storage costs or server costs that might be a concern you should understand. Though typically it's not something to worry about for the pages you create in the course or on your own for personal use. When you want to include images in the pages you create, it's easy to use Google Image Search to find images online. You'll need to find the URL for the image to use in the inline link for the IMG tag. You can typically find the URL by right-clicking, sometimes this is control-click, when using a web browser like Chrome or Firefox, and then copying the image URL and pasting it into the HTML you're creating for your own page. Some websites won't allow you to hot link to images stored on them. For example, Pixabay hosts many public domain images, but will not allow you to link to them in the web pages you create. You should be sure to test the web pages you create so that they work. You may use incognito or private browsing to be sure that you are behaving like an anonymous user rather than being logged in as yourself, for example, when looking at a web page. When you can, get someone else's help in viewing any web pages you create to be sure that they see the images.
You've already learned some basics of HTML, which lets you specify the contents of a web page that you want to make. You learned about metadata tags, such as head and title, and sectioning tags, such as body, H1, and H2. You learned about text content, such as the p tag, which formats a paragraph. However, there's much more that you can do with HTML besides just put text into paragraphs. One way that you might want to organize information is in lists or tables, which we will explore now. We use bulleted lists often when presenting information. In fact, much of the content of these video presentations presents information in that form. Here, you can see a screenshot from a sample web page that organizes information into a bulleted list. This particular style of list is called an unordered list, which you can create with the UL tag, which stands for unordered list. Even though the list is called unordered, the content still appears in the order that you specify it. It is just called unordered because the labels are all the same bullets by default. Later in this lesson, we will show you how to create lists with numbered items. When you go on to learn about CSS, you can change the style of the bullets. Now that you have the big idea, let us dive into the details of using the UL tag to make unordered lists. Here's the HTML for the page we saw a second ago. If you look inside the UL tag, which corresponds to the actual bulleted list, you will see many LI tags. Each LI tag, which stands for list item, describes one item in the list. If we look at each of these LI tags, we can see how they correspond to the items that appear in the list. When you make lists, it is important to know that you must place everything in the list inside LI tags. All of the tags inside of the UL tag, called the UL tags children, have to be LI tags. Otherwise, our HTML is incorrect. However, inside the LI tags, we can put much more than just text. We can put images, links, or even another list. Okay, so you know about unordered lists. But sometimes you want an ordered list, one that will number the items. If you wanted to describe your preferences for your 5 favorite fruits, for example, you might want to number them. In such a situation, numbering is important as you want to indicate the ordering of the list. You can also have lists which are ordered but labeled with letters instead of numbers. You can make these types of lists with the OL tag, which stands for ordered list and works a lot like the UL tag. Much like the UL tag, you specify the list items with LI tags, which are the only type of tag you can put as direct children of the OL tag. Of course, as with the UL tag, you can put a lot of different kinds of things inside of the LI tag. The numbering for LI tags is automatic. If you add or remove elements from your HTML, the numbers will automatically adapt so that the elements are numbered 1, 2, 3, 4, and so on. We mentioned how you can put a variety of types of elements inside of an LI tag, letting you put images, links, or nested lists inside of a list. We call putting these elements together composing them. Composition is an important concept in computer science and is common in design of languages, whether markup languages like HTML or programming languages like Java. This property lets you build large complex systems, whether web pages or programs, in a way that you can understand. You can put small, easy to understand pieces together to build larger, more complex things. In the case of web pages, we can put elements together to get more sophisticated formatting. In most cases, you can compose elements with each other however you want, although there are some rules. For example, you cannot put the title tag inside of an unordered list because it does not make sense for the title of the page to be inside a list. The title tag can only go in the header. However, you can make a list of images or a list of lists. When you make a list of lists, it is called a nested list. Nesting is another common concept in computer science, which just refers to one of a thing being inside of another of that thing. Here, you're going to learn about nested lists. Later, when we delve into programming, you will learn about nested loops. The concept is the same, a loop inside of a loop, much like a list inside of a list. You can make a nested list, such as this one, by placing a UL tag, which describes the inner list, inside of the LI tag for one of the items in the outer list. Notice how the bullets for the inner list are different from the bullets for the outer list, as well as how the inner list is indented more deeply. These features both help whoever is reading the web page visually distinguish the content in the outer and inner lists, as well as when you write the HTML, it is helpful to indent more deeply each time you put one element inside of another. This structure helps you visually distinguish where elements belong in the HTML so you can edit it more easily later. Notice how you can compose the list items here. You just write the inner list with UL and LI just like you would do anywhere else. You do not have to do anything special, and that is an important aspect of composition. You just put the pieces together and they work the same way everywhere. The HTML for this example is available on CodePen if you want to play with it after you finish watching this video. Another way you might want to organize information in your HTML is with a table, which lets you arrange things into rows and columns. For example, you might want to display some information about food based on what taste you associate with it. Sometimes people will use tables for more general organization of the contents of the page, but CSS, which we will learn about later, is the preferred way to do that. You make a table with HTML elements that match up with the visual structure of the table. Now, let us look in depth at the HTML elements that were used to make this table. First, you write a table tag at the start of the table, which has a matching int table tag at the end of the table. Next, you write a tr tag, which stands for table row, for each row of the table. As you can see here, each tr corresponds to one row in the resulting table. Rows can either contain th tags, which specify header elements, such as these, and td tags, which specify the data for non-header elements of the table. We have text inside of our td tags here, but do you think that you could put other things inside of them? Sure, the principle of composition says that you could put images, lists, or a variety of other things in your table if you wanted to. Okay, so now you've seen HTML tables and lists, which let you organize information, from simple to complex. If you wanted, you could put a table tag inside of an LI tag, or a list inside of a table. Isn't composition great? You're going to see it come up again as it is a key principle in computer science. And it will help you as you create, design, and build whatever you want the computer to do for you, whether it is a web page to show off some cool information or a program to compute something important.
Web pages today are displayed and experienced differently depending on many criteria. The kind of device and screen affect both how to display and what to display. Web pages are often designed to accommodate different users with different abilities and disabilities. Users experience web pages differently. Some users are colorblind, some can't see well, and some have a hard time clicking on small links. Users may see web pages on computer monitors, but today, many users are viewing the web on mobile devices like smartphones and tablets. Web pages may even be displayed on huge screens. Web designers must take users and devices into account when creating web pages. Even as you learn the basics of web page creation and design, you can and should keep some things in mind when you create a web page, working to make web pages accessible. You'll do this by removing barriers and to help make your web pages accessible to everyone. Some people have trouble seeing certain colors, some can't see at all, and some have a hard time manipulating a mouse. Users with poor eyesight may use screen readers to help view and experience a web page. Some colors and some fonts are easier to read than others. Some alphabets require special fonts to display well. If you develop more web pages, you'll want to ensure a good user experience, and this means that pages should load quickly when that's possible. We've already used HTML, or hypertext markup language, to create web pages that anyone in the world can see. HTML specifies the content of a document, the words and images that appear in a web page. Some formatting is specified with HTML. For example, different size headers are indicated in HTML by H1 or H2 or H3 tags. Different kinds of lists are indicated in HTML by using OL and UL tags for ordered and unordered lists. These display differently because browsers interpret the HTML and change both headers and lists to match the HTML markup. Tables are also formatted using HTML, as you've seen, with the many tags that are used to build a table for displaying data and other information. Images are displayed using HTML, and you've seen that the width of an HTML image, or IMG tag, can be specified using the width attribute or specifying the width using a style addition to the HTML tag. These style and width modifications are example of what's called CSS to style a web page. CSS is an abbreviation or an acronym for Cascading Style Sheets. CSS specifies the look and formatting of a web page, whereas HTML specifies the content. This allows web designers to separate the content from how it's presented, which can accommodate different users and different display devices to make sure that even in other countries, these can be displayed without changing the content of the web page. For example, how big is an H1 header tag? What color should be used for the text in an H1 header tag? Should the color or size depend on the user and how the user is experiencing the web page? On whether the user is using a mobile device? These attributes of a tag can be specified and changed using CSS. If you're creating thousands of web pages for a website, changing the color or font or the size of an HTML element can be localized in one place, rather than repeated in 1,000 places, which would make changes difficult. Design for scale is a key part of computer science, and one that CSS and HTML together make possible.
Now you're going to learn a bit more about CSS. Last time you learned why you would want to use CSS to separate the style of a web page from the content, which touched on some major themes in computer science. One of those themes was reusability. You can describe a style once in CSS and reuse it across multiple elements or even multiple web pages. Another of those themes was maintainability, being able to efficiently change your web page in response to changing design requirements. Now that you have learned a bit about why CSS is important, we are going to build on that and delve into how you can write your own CSS to style a web page. Before you learn what to write for CSS, we are going to teach you where to write it. In CodePen, you've been writing HTML in the left pane. To the right is the CSS pane, which I have highlighted with a blue square here. You can identify it by the fact that it says CSS in the top left corner of that pane. Also, don't worry about the slightly fancy CSS in this window. It makes a nice looking table, but you only need to learn the basics. If you were writing a web page from scratch without a tool like CodePen, you could include CSS by either using the style tag and writing the CSS inside it, or by using the link tag to link to a style sheet. Either of these tags go in the head portion of your HTML. We will start with the small example web page shown above, which describes some delicious foods. On the left, you can see the web page with no CSS. Notice how the header, drawn by the h1 tag, is in black text and left aligned. Now suppose that you wanted to make that header blue and center, like the one on the right. This page on the right has the same HTML, but we have used CSS to change the formatting of the h1 tag. Here is the CSS we used to style the h1 tag to be blue and centered. Let's look at it in detail so you can write your own CSS to style the pages however you want. The first thing you need to write is the selector, the name of the element that you want to style. In this case, we wanted to style h1 tags, so we write h1 here. Next, you write curly braces, which surround the style information you want to apply to the h1 tag. When you write an open curly brace in CodePen, it will automatically put a closed curly brace after it and put your cursor between them. This behavior can be helpful as you do not have to remember to write the closed curly brace after you finish writing the style you want. On each line inside the curly braces, you first write the property, what aspect of the styling you want to change. Here we want to change the text alignment, which has the property name text align. After the property name, you write a colon, followed by the value you want to give that property. In this case, we want to set text align to center. At the end of the line, you write a semicolon. You can then write more lines with the same syntax. For example, we have color, colon, blue, semicolon to set the color property to blue. There are many properties you can set in CSS. We won't go into all of them here, but rather suggest you might read more about them online as you need them. As with many things, you should not try to memorize them. Rather, look them up as you need them. If you end up writing a lot of CSS, you will become familiar with the properties that you use often. In your in-video quiz, you just thought about how this CSS styles list items to be green. However, this CSS makes all list items in your entire web page green. What if you wanted to make some of them green and style some of them a different way? We're going to show you 3 approaches to styling only some of a particular element. The first way you might do this is to use a class, a named style. To use a CSS class, you need to change your HTML by writing class equals and the name of the class you want in the tags you want to style. Now in your CSS, instead of writing the name of an HTML tag as a selector, write a dot followed by the name of the class. The dot specifies that you are naming a class. Immediately after the dot, you should write the name you want to give the class. This name can be pretty much anything you want. It has to follow some rules, like you can't put braces or spaces in the name, but you can pick any word you want for a name. However, you should make the name descriptive. In this example, we picked food li, since we're using the class to style list items that describe food. Would .green be a good name for this class? Even though that describes how it styles the list items right now, naming it .green is not a great choice. If we later decided we wanted to style our food list items to be purple, our style name would be misleading. Instead, we're better off naming it based on the meaning of the parts of our page, and we want to style food list items. If you look back at the HTML, now that you've seen the CSS, you can see where the name we picked came from. It matches up with the class name we picked in our CSS. Another way to style only some of a particular element type is to use an ID. An ID names one particular element. Notice the difference between a class, which can be applied to many elements, and an ID, which can only be applied to one element. In this example, the web page has a picture of a cake, which we want to style in a particular way. We have specified ID equals cake IMG inside the IMG tag. Now in the CSS, we can describe the styling for cake IMG. Notice how the selector for an ID starts with a pound sign. The final way that we will mention, but not go into depth on, is called combinators. These let you specify relationships between tags. You might specify that you want to style LIs that are inside of ULs in a particular way, which you could do by writing UL LI as the selector. There are more advanced relationships such as siblings. Combinators are a more advanced topic which you do not need to know, but we mention it for those of you who want to explore a bit more. Classes and IDs both let you name a way to style an element. Naming a style lets you reuse that style as needed. In the case of a class, you can style many elements on a page in the same way. For both names and classes, you can reuse a style across multiple pages. For example, if you have a logo that you want to display in the corner of every page on your site, you can write a style for it once and reuse that style on every page. Naming and reusing is a common theme in computer science. As you delve deeper into programming, you will find that it is often useful to name things, constants, algorithms, or data, so that you can reuse them. Now you have seen the basics of CSS. You've learned where to write CSS in CodePen, the basic syntax of CSS, and how to make classes and IDs to name and reuse styles. In this lesson, you are going to learn a bit more about CSS. In the last lesson, you learned the basics of CSS, its syntax, as well as how you can name styles with classes and IDs. In this lesson, you're going to learn a bit more about colors in CSS. In particular, you will learn that you can specify them not only by name, but also by numeric values. An instance of an important concept that you will learn in the next lesson, that everything is a number for a computer. Remember from last time that you learned to style the H1 tags to be blue and centered. We use blue as the value for the property color to achieve this styling. What if you wanted to use another color? We saw green in another example, so you could guess that you might be able to use a variety of basic colors such as red and yellow, and you would be right. But you might want to design a web page with more sophisticated color choices. CSS supports a much wider variety of color names, giving you the ability to choose some nice shades of different colors. Here's a few of my favorites. Blue violet is a nice shade of purple. Gold is of course gold colored. Light blue steel is a nice bluish gray. And fire brick is a deep red. In fact, there are 140 standard color names, giving you a wide selection of colors to choose from by name. How could you remember them all? As with many other things, nobody memorizes these sorts of things. Instead, what's important is knowing how to look up what you need. You can find websites such as this one, which will show you the various colors as well as their names. However, even 140 colors is not a lot. What if you wanted some other shade of a color that does not have a standard name? It seems like we might want more colors, but how many would we need? Humans can perceive literally millions of colors. For example, we have here 12 very subtly different shades of blue, ranging from very dark on the left to a medium light blue on the right. These are just a few shades of blue, and one of them is a very important shade of blue. This bar in the middle is Duke blue. Of course, there's many more shades of blue and many more shades of other colors too. So how could we handle millions of colors? Giving them all names would be somewhat unmanageable. One problem is that someone would have to come up with millions of color names and standardize them. Another problem is that you would have to look through millions of names to find the color that you want. Limiting the selection of available colors is not a very appealing option. If you really want a particular color, such as exactly Duke Blue, you would be unhappy if you could not get it. Another option would be to give each color a number, which is what is actually done. In fact, as you will learn later, for a computer, everything is a number, so this choice is actually a natural way to handle millions of colors. The way that colors work as numbers is that they are specified by a combination of how much red, green, and blue they have, with each component taking a value between 0 and 255. This scheme is sufficient to specify about 16 million colors, which is more than humans can distinguish. In CSS, you can specify a color by specifying its red, green, and blue components by writing RGB, then in open parentheses, followed by the numerical value for red, green, and blue, each separated by a comma, then a closed parentheses. This syntax takes the red, green, and blue numbers and then combines them into a single numerical value for you. Each of the colors we saw before has their RGB values written on top of them here. You can also specify a color by its entire numerical value by writing a pound sign followed by 6 hexadecimal digits. Hexadecimal means base 16, so each digit has a value from 0 to 15. Hexadecimal is convenient to write RGB values since each color has 256 possible values, meaning exactly 2 hexadecimal digits. The left 2 digits here specify the red. The middle 2 digits specify the green, and the right 2 digits specify the blue. You do not need to be able to convert to and from hexadecimal, but for those who are curious, we will take a closer look. You're used to base 10 numbers where each place is 10 times the previous. You have the ones, the tens, and hundreds places, and so on. In hexadecimal, each place is 16 times the previous, so you have the ones, the 16ths, 256th place, and so on. If we look at the 2 digits for each color, we have the ones and 16ths places. The red of this color is 8A, which is 8 in the 16th place, plus A, which is 10, in the ones place. That makes 138. For the green, you get 2 in the 16th place, plus B, which is 11, in the ones place, which makes 43. For blue, you have E, which is 14 in the 16th place, and 2 in the ones place, which makes 226. Many people find it easier to choose colors graphically and let a tool give them the number. Let us see an example of this with Mozilla's Color Picker. This is the Color Picker tool available from Mozilla. You can see the URL of this tool at the top of the web browser here, but you can also find a link to it in the reading that goes with this lesson. As we look down at the main part of this tool, you will see it has a colored box and a colored slider. Moving this slider around, adjust the hue of the color. You can see red, yellow, green, blue, purple, and red. Maybe you want a shade of, say, purple. You can then adjust the specific shade in the box on the left. You can get grayer, or brighter, or lighter, or darker. I'm going to pick this color. Once you find the color you want, this tool displays the numeric information to the right. For this shade of purple, the red is 232, the green is 73, and the blue is 227. You can also read the entire hexadecimal number from this box on the bottom. It's E849E3. There are some more advanced features, such as alpha, which lets you adjust transparency in case you are layering objects. If you wanted to use that, this other slider would let you change the transparency. The tool also shows HSL, which is just a different way to represent colors as numbers, but we won't worry about that. So if you want to pick a specific color graphically, a tool like this can be really great. That concludes our lesson on colors in CSS. You have learned that there are many standard names, which you can look up when you need them, and that you can specify millions of colors by numerical values, either by writing RGB and the red, green, and blue values that you want, or by writing a pound sign and the hexadecimal value of the color's number. We also saw a color picker tool, which lets you look for the color you want to use and then gives you the numerical values for that color to write in your CSS.
So far, you've been looking at making web pages. Now, we're going to switch gears for a while and start learning about computational thinking, the type of thinking that enables you to write computer programs. You'll be programming in JavaScript so that eventually you can use your programs to enhance your web pages. In this module, you'll learn some basic programming concepts and JavaScript syntax, a process for designing algorithms or solutions to programming problems, and how to work with some image processing libraries we've developed for this course. So why are you learning programming? What can you do with it? Programming is great for solving problems that have a lot of computation or repetition in them. For example, what if you wanted to manipulate the images on your web page? Since images are made up of pixels, to manipulate the images on your web page, you would need to look at all the pixels in them. If you had an image that was 100 by 100 pixels, a relatively small image, you would still need to look at 10,000 pixels. This is hard for humans, but easy for computers. If you tried to look at all 10,000 pixels by hand, you might get bored, you might make mistakes, and it would definitely take you a long time. A computer could finish looking at all 10,000 pixels in just a few seconds. One common application of image processing using programming is using green screens to change the background of an image. If you take a photo in front of a green screen, you could write a program to change every green pixel in the image so that you replace the green screen with another image. This is the example you'll focus on in this module. You'll learn our 7-step process for solving problems, the basics of JavaScript, and the programming concepts you'll need to be able to solve the green screen problem and many more. Now, let's start by looking at one important idea behind programming, that everything is a number. Welcome back. In this lesson, you're going to learn an important principle of computer science. Everything is a number. Or, put a different way, computers only work with numbers. If we were to delve into the hardware, we would find that it only deals with bits, zeros and ones. We're not going to look into the particulars of the hardware, but the important thing to know is that computers can only work with numbers, and really can only do math. In fact, there's nothing that a computer can do that you cannot do. Computers can just do math really fast, so they can operate on large sets of data billions of times more quickly than you or I could by hand. Fortunately, you do not typically need to think about the details of the bits due to a wonderful principle called abstraction. Before we talk more about how everything is a number, we'll take a minute to talk about abstraction. Abstraction is the separation of the interface, what a thing does or how you use it, from the implementation, how it does that or how it works. You can understand abstraction and its usefulness with a non-computer related example. Think for a moment about driving a car. Abstraction lets someone drive a car without knowing how it works. I know that if I press down on the gas pedal, my car will go faster. However, I do not know about the complicated inner workings of my car that make that happen. Abstraction often comes in layers, and what layer you need to work at depends on what you need to do. For someone driving a car, the level of abstraction appropriate to think about is what the controls of the car do. The inner workings under the hood are hidden and not important. However, for a mechanic, the details under the hood are important and are what she works with day to day. But even there's a different level of abstraction. The mechanic is concerned with how the parts of the engine fit together and work together, but maybe not with the physics that go into designing the engine. The engineers who designed the car would have worked at that level of abstraction, applying physics to make a car that works properly. Of course, there is an even lower level of abstraction in a more theoretical physics that they did not concern themselves with. We could keep going down until we reach the most theoretical physics at the boundaries of human knowledge. All things that you do not need to know to drive a car. These same concepts apply in programming. The level of abstraction that you need depends on what you are doing. Before this class, you have probably used a computer without knowing anything about how programs work. Now you will learn how programs work, but there will be deeper levels of abstraction that you generally will not need to know about. Now that you know about abstraction, let us return to the principle that everything is a number, giving you a bit of a peek under the hood. You may be a bit surprised by this idea since you're used to using your computer working with things that do not seem like numbers, such as letters. However, these are relatively easy to encode as numbers. We could go with A equals 1, B equals 2, and so forth. What computers actually do is represent characters, symbols that can be letters, digits, punctuations, and so on. One way to encode characters is ASCII, in which capital A is 65, lowercase a is 97, exclamation mark is 33, and various other characters have other numerical values. If you needed to look up the numerical value of a character, you could find them in an ASCII table. However, you generally do not need to worry about the particular numerical values due to the joys of abstraction. Once we have characters, we can also have strings, sequences of characters, such as hello! Exclamation mark. Strings come up quite often in computer science as programmers frequently want to manipulate text. In fact, you've seen strings in HTML. Strings are another great example of abstraction. You can write hello! Exclamation mark, and it gets turned into numbers that your computer can work with. You generally do not have to think about the numeric representation, but you can manipulate it if your programming task calls for it. So why is it so important to know that everything is a number? Well, sometimes you want to do math with things that do not seem like numbers. Cryptography, the science of keeping information secure, relies on the ability to do math on strings. When you visit a website using HTTPS, the information sent back and forth between your computer and the web server is encrypted so that nobody else can read it. That process involves doing math on that data. Another reason that it is important to understand that everything is a number is because this is why programming languages have types, which tell it how to operate on these numbers. Even though everything is a number, programmers want to interpret those values in different ways. Do the numbers mean letters? Do they mean pictures? Do they actually just mean plain numbers? The type of the data tells what the numbers mean and thus how to operate on them. If we add two strings together, we might want to concatenate them. Put one after the other to form a longer string. In that case, the string 1 plus the string 1 would be the string 1, 1. If we have just the number 1 and we add it to 1, we would get 2. A third reason why the everything is a number principle is important is that whenever you have data you want to work with, you need to represent it as numbers. You may be able to use existing types, such as strings, which already represent information as numbers, to help you out. Such is the joy of abstraction. One other thing that may surprise you is that programs themselves are numbers. Then again, it may not surprise you, since you just learned that everything is a number. As you have already seen, you express your algorithms to the computer by writing text. The code that you type in is a string. Another program takes this string and figures out how to turn it into numerical instructions that the computer can execute. The fact that programs are numbers is actually quite powerful. It means that you can download and run new programs on your computers. They're just data like everything else. The fact that programs are also just like data is at the heart of many security issues. Hackers give program input that have the numeric encodings of instructions they want to execute and then trick the program into running it. Of course, as you write programs, you do not need to worry about the numerical encoding details, all because of the wonderful ideas of abstraction. So in this lesson, you learned that everything is a number, an important principle since computers can only do math. You learned about abstraction, the separation of interface from implementation, and how that means that you may not always need to think about how things are numbers to compute with them.
Hey, Drew. I remember in the last lesson you taught us that everything in the computer was represented with numbers.
Sure, Robert. This is a very important principle in computer science, as computers can only compute on numbers.
I remember, and it was really cool you showed us that we could represent letters and logic with numbers. But I have so much more on my computer than just words. For example, look at all of these images. Surely they're not just numbers.
Actually, Robert, if we were to zoom in on one of these images, we would see that it's made of many tiny little dots called pixels. Each pixel is a single color and is numerically represented by a red component, a green component, and a blue component. Each of these values ranges from 0 to 255, where 0 means none of that color, and 255 means as much of that color as possible. Once we've represented each pixel as a number, we can represent the entire image with thousands or millions of pixels, meaning thousands or millions of numbers.
Wow, that's really cool. But if they're just numbers, we could do math on them. If I had magenta and I had green, could I add them together?
Sure. Let's see how. We can do math on colors because they're just numbers. To answer Robert's question, if we took magenta, which has a red value of 255, a green value of 0, and a blue value of 255, and added it to green, which has a red value of 0, a green value of 255, and a blue value of 0, we would get a red value of 255, a green value of 255, and a blue value of 255, which would be white. In fact, we can solve a lot of useful problems by doing math on the pixels that make up images. We could make an image lighter, darker, redder, or bluer, or we could compress an image so that it takes less time to transfer across the internet while still looking the same to the human eye, for example, a JPEG file. If you've ever heard of a movie codec, this is software that encodes and decodes video, doing a lot of math to determine the images that make up each frame of the video.
That's really neat. So do you think that I could write an algorithm that would replace all of one color in an image with a completely different image?
Sure. In fact, that's what's happening to us right now since we're standing in front of a green screen. The video software is iterating over all of the pixels in our images and replacing green ones with a different image. We could, if we wanted to, give this lesson in front of dinosaurs or even in outer space.
That's really amazing. I'm going to go write the green screen algorithm for practice right now.
Produced by Duke University. Online at duke.edu.
The green screen problem, also called a chroma key problem, because it is keyed to the color's chroma, or hue, like removing the red from eyes in a picture taken with a flash, is common in videography as it allows actors to be recorded in a studio and placed in front of a background or made from an image or video taken in another setting. This algorithm is what let Drew and I talk in outer space with dinosaurs. Now we are going to walk through solving this problem as an example of how to approach programming problems in general. The first thing we need to do before we solve a programming problem is to figure out exactly how to solve that problem ourselves. You cannot write a program, explain to the computer what it needs to do, until you completely understand yourself how to do the task in a precise step-by-step fashion. In fact, this is often the hardest part of programming. Now, trying to do this particular example of the green screen problem would be too difficult because these images have 2 million pixels each, approximately. Trying to operate on them by hand would take an impossibly long time. Instead, it is a good idea to work on a smaller instance of the problem by hand to gain a deep understanding of how to solve the problem. In this case, we're going to look at a 2 pixel by 2 pixel image. We will start by picking a 2 by 2 image to be the foreground, the image that will go on top, and we'll pick a 2 by 2 image to be the background. Also, we will need an image to hold the final result, or output. This should also be 2 by 2. Now that the examples are chosen, let's go through and figure out what color to make each pixel of the output image. Great! Now we have solved an instance of the problem by hand. The next step is to write down exactly what we did in a step-by-step fashion. I started with the foreground image I wanted. I'll call this FG image. And with the background image, I'll call it BG image. I then made a blank image of the same size. I'll call it output. I looked at the first pixel in FG image, and it was red. So I set the output's corresponding pixel to be red as well. I looked at the second pixel in FG image. It was green, so I looked at the same position in BG image and set output's corresponding pixel to BG image's pixel. I looked at the third pixel in FG image. It was green, so I looked at the corresponding pixel in BG image. It's blue, so I set the output to be that same color. I then looked at the fourth pixel in FG image, and it's blue, so I set the corresponding pixel to be blue in the output. Great! Now we have a step-by-step set of instructions to describe exactly how we solved the problem for this particular pair of images. But to write a program, we want to be able to solve this problem for any image of any size. Now, if you look at these steps closely, you will see that there is a lot of similarity. We're doing almost, but not quite the same thing for each pixel in the image. When the FG Images pixel is green, we use the BG Images pixel. And when the FG Images pixel is not green, we use the FG Images pixel directly. Going back to our step-by-step instructions, we will rewrite each step to be a little bit more general, taking into account this conditional behavior we just observed. You can do this for each pixel's step. And now each step is more general and more similar. They would work for any 2x2 images, but only for 2x2 images. Here we've improved the step-by-step instructions to express the repetition over each pixel. Now the steps are general enough to work on any sized image. In fact, what we have done is devise an algorithm that we're going to implement. An algorithm is a clear step-by-step set of instructions to solve any instance of the problem you want to solve. You can express an algorithm in English, as we have done here, or in code, as we'll need to do to let the computer run it. Everyone makes mistakes. When devising an algorithm, there are many different ways to make mistakes. For example, you may not have seen the pattern correctly, or you may not generalize each step correctly. To try to protect against these types of mistakes, let's try our algorithm out on a different example to see if it works as expected. If it does, we'll be more confident that we did it right. If not, we've caught our mistakes early before we went to write code. Of course, once we write code, we will want to test it more thoroughly, but we'll talk about that later. As you walk through your algorithm, you will want to keep track of what step you're on. For us, we're going to draw a green arrow to show where we are in the algorithm. You then want to go through each step exactly as it is written. Here I've picked the 3x1 image to be the foreground, and this 3x1 image to be the background, and a 3x1 image to be the output. Here I will keep track of which pixel is the current pixel with a blue arrow in the drawing above. This first pixel is green, so the algorithm says to look at the same pixel in the background image, which is yellow, and make the same pixel in the output image also yellow. Those are all the steps for that pixel, so now the algorithm says to go to the next one and repeat the process. We will continue to follow these steps as they are written, exactly as they are written, until we finish all of them. At this point, we want to see if the image came out as expected. In this case, the output was right. Since our algorithm appears to work, it's time to write the code.
Now we're going to talk a little bit more about solving programming problems. In the last lesson, we worked through the example of doing the green screen problem. We took a specific problem we wanted to solve, taking images and applying the green screen technique to them, and worked through step by step how to go from that problem statement to a working piece of code. Now, what we're going to do in this lesson is we're going to take a closer look at solving programming problems. We're going to teach you the 7-step approach that you're going to use to solve programming problems through the rest of this course and the rest of this specialization, as well as a tool that you can use to solve programming problems in general whenever they come up in the rest of your life. In general, solving a programming problem starts with a problem statement. I want to be able to take a foreground image and a background image and combine them using the green screen technique or anything else you might want to do. And ends when you have working code that solves your problem. Now, doing this is a big leap. It takes a lot of work to go from a problem statement to a working piece of code, and you may not be able to just do this in your head all at once. Sometimes, when a problem becomes easy for you as you become more skilled, you'll be able to just do this, and it will happen naturally and you won't need to worry about it. However, the 7-step approach we're going to teach you is always going to be a good way to approach any problem where you can't just see the answer right away. So these are the 7 steps that you're going to use to solve programming problems, and we're going to look at each of them and see how they work. You've seen this already with the green screen example. We just didn't talk about the details of each step, we just did the process. The first thing to do is to solve a small instance by hand. If you remember from the green screen lesson that we just did, we took a 4-pixel image. We didn't want to start with the millions of pixels that are in a real image. We just worked through for a very small instance, something manageable. If you have trouble with this step, maybe the problem is unclear. The problem statement doesn't actually tell you how to do things. in which case you need to find out what you're supposed to do before you can proceed. In a classroom situation, this may involve asking your teacher or teaching assistant for clarification. In the real world, this may involve talking to your technical lead, your customer, or refining the problem yourself to figure out exactly what it is you need to do. The other possibility, if step 1 is difficult, is that you might need domain knowledge. If you're trying to solve a programming problem related to physics, but you don't know the physics equations involved, then no amount of programming expertise will help you. You need to consult a physics textbook, a Wikipedia article on physics, or a physics professor to understand the physics before you can try to solve your programming problem. Once you've completed step 1, you're ready to proceed to step 2. In step 2, you're going to write down the exact steps of what you did in step 1. That is, you're going to give directions to someone to solve just that instance of the problem. Not to solve the more general case, not to do it for any image, but just how you came up with your answer for that particular 4-pixel image or whatever your problem might be. The tricky part here is that there are a lot of things that we as humans do without consciously thinking about them. We just kind of naturally do them, and we have to think really carefully because the computer doesn't have common sense. We need to be very precise. If we're a little sloppy with our steps here, it's going to make things more difficult for us later on because we're going to be missing crucial parts of our algorithm. In step 3, we need to find patterns. We want to write an algorithm for any instance of the problem, not just the particular instance that we worked. And so what we're going to do is look at the steps that we wrote down in step 2, and we're going to find patterns. We're going to think about repetition. What things are we doing over and over again? How many times are we doing them? These will lead to looping constructs. Conditions. Sometimes we do something, sometimes we don't do it. Under what conditions does this happen? This will lead us to conditional constructs like if-else. And we'll have values. Maybe we used a particular number because it was part of our input or related to our input. We need to think about why we used that particular number. If we have difficulties in this step, we need to go back to steps 1 and 2 and do them again for different inputs. If we do these over and over again, we'll come up with more information to look for patterns from. We'll have different sets of steps that we come up with for step 2 that tell us how we worked multiple instances of the problem and be able to find patterns more easily. Once we finish step 3, we want to check our algorithm by hand. We just came up with what we think is a general algorithm, but we may have made a mistake. We may not have realized that something happened under a particular case, or we may have left a value that was particular to the parameters that we chose. If we did one of these mistakes, we'd like to find this now before we translate our algorithm into code. So we're going to check this with one or more different inputs, which are again going to be of sizes that are manageable to do by hand. We're not going to try it on 1,000,000 pixels, but we might try it on a very small other image or some other small input. Once we're confident in our algorithm, we're ready to translate it to code. This is where the particular programming language that we're working in is going to come into play. So far, we've been looking at JavaScript, so we would take our algorithm and express it in the syntax of JavaScript. Once we've written this down, we want to run test cases. That is, we want to execute our program and see, did we get the right answer with our program based on what we expect the right answer to be, knowing what problem we're trying to solve. Every time we run a test case, if it passes, that is, we get the right answer, we're more confident in our program. If it fails, we know something is wrong with our program, and we move on to step 7, debugging failed test cases. For this, we're going to use the scientific method, which we're going to talk about a lot in the next lesson. And this is going to help us understand what the problem is and give us guidance on what we need to do to fix the problem. Ultimately, what's going to happen is if we have an algorithmic problem, we're going to return to step 3 and fix our algorithm. And if we have an implementation problem, we're going to return to step 5 and correct our translation of our algorithm to code. So these are the 7 steps that you can use to solve any programming problem, and we're going to use them throughout our examples in the rest of this course and specialization. Okay, now that you have the algorithm for green screening an image, you want to translate it into code. but you have a lot of different pieces of code that you need to learn. We're going to learn these in JavaScript now, but the same basic concepts exist in pretty much any programming language. We'll switch to Java in the next course, and you'll see that much of this looks the same. One thing you need is a way to give names to the values your algorithm comes up with. In the English description, we refer to them as FGImage, BGImage, output, and current pixel. These are going to turn into variables in your code, which you will learn about momentarily. You also need a way to make images, whether reading in an existing image or creating a blank image. You need a way to operate on these images and their pixels, looking at particular pixels, seeing what color they are, and setting the pixels in an image. You'll learn about these soon. Your algorithm calls for you to repeat some steps for each pixel in an image. You're going to need to learn how to write code that repeats steps, which will be a for loop, which you will learn about later. And finally, your algorithm looks at a condition, in this particular case whether a pixel is green or not, and makes a decision about what to do next based on that condition. This is going to turn into an if-else statement, which you will also learn about soon. Here is an example of a JavaScript statement which declares a variable called x and initializes it to 3. Declaring a variable means telling JavaScript that you want it to make a new variable. Initializing a variable means giving it the first value that it should hold when you create it. Some languages do not require you to initialize variables, but it is a good idea to always do so. Let us take a minute to break down the syntax of this statement. First is the keyword var. This keyword is what tells JavaScript that you are declaring a new variable with this statement. JavaScript is case sensitive, so you have to write var in all lowercase, otherwise it does not recognize it as this keyword. Next is the name of the variable. In this case, we picked x for the variable's name. You can name variables pretty much anything you want. There are some rules, but they're somewhat complicated. If you stick to letters, you'll be in great shape. While we can name your variable anything, it's good to name it descriptively. Here, we are not using the variable as part of a real algorithm, so we can't give it a really meaningful name. However, remember that we called the variables in our green screen algorithm things like FGImage, BGImage, and output, which indicated what they were for. Next is an equal sign. This equal sign indicates that we're going to assign a value to the variable. After the equal sign is the value that we want to assign, in this case 3. Finally, there's a semicolon at the end of the statement. In JavaScript and many other programming languages, semicolons are used at the end of statements, much like periods are used at the end of a sentence in English. You might wonder why programming languages don't end statements with a period, since that seems more natural. However, periods get used for a lot of other purposes, such as decimal points and numbers, which would make it hard for the computer to figure out if a period ends a statement or serves some other purpose. Now that you have seen the syntax, let us take a look at the semantics. Recall that semantics are the meaning of something. In the case of a programming language, the semantics are the meaning of what the code does, what you're telling the computer to do. We're going to keep track of where we are with the green arrow shown here, just before the start of the code. This arrow will typically point between statements, indicating that we have finished the previous statement, but not yet started the next statement. We will move it across a statement as we do the effect of that statement. Here, we are declaring a variable called x and initializing it to 3. So the effect of that statement, its semantics, are to create a box labeled x and put 3 in as its value. Here is a slightly larger example with 3 variables. The first you just saw. We create a box labeled x and put 3 in it. The next statement is pretty similar, except the variable is named y and is initialized to 4. So to execute this statement, we would create a box called y and put 4 in it. The final statement is a bit more complex. It declares a variable called z, but the right-hand side of the equal sign has a more complex expression to compute the initial value, x plus 2 times y. Expression is the technical term for a combination of values and operations to compute a value from them. Here we have a mathematical expression involving the variables we previously declared, so we just do the math. To get the value for x, we look in its box and find that x is 3. Likewise, to get the value for y, we look in its box and find that y is 4. Now we just have to compute 3 plus 2 times 4, which is 11. So we will create a box named z and initialize it with the value 11. You can also update the value of an existing variable with an assignment statement. Notice that the syntax is fairly similar to declaring a variable, except that you do not write var since you are changing an existing variable rather than making a new one. Instead of creating a new box, you will update the value in an existing box, in particular, the box named on the left side of the equals sign. Here, we're going to do x equals z minus 1. So we would compute z minus 1, which is 10, and update x's box to be 10. The next statement says y equals y times 2. This looks like an equation from algebra class, and sometimes novice programmers think that this statement would solve an algebraic equation. However, that is not the case. This statement follows the same rules as any other assignment statement. The current value for y is 4, so we compute 4 times 2, which is 8, and update y's box to be 8. Okay, great. Now you have seen the basics of variables with some numeric values. But what if you want variables that hold things that are not numbers? How could you do that? Well, remember, everything is a number. So under the hood, every variable is actually a number. But you can use other data types like images and strings where the numbers are interpreted in other ways. Let us look at this example. We have two statements here, each of which declares and initializes a variable. The first declares fgImage and initializes it to a new simple image, which would have the effect of creating a box named fgImage whose value is this image of me and Robert. You may notice that the image is not directly inside of the fgImage box, but rather off to the side with an arrow pointing at it. When you do new, you end up with an arrow pointing at the thing that new made. Why does it matter that new makes a thing and that the box has an arrow pointing at it? As you will see soon, you can have multiple arrows pointing at the same thing from different boxes. The second statement behaves similarly, except that the image which bgImage is initialized to is dinos.png. The expression that we are using to initialize these variables is a bit more complex than the mathematical expressions we saw earlier. So let us delve into them for a second. First, we have the keyword new. This tells JavaScript to go create a new object. What is an object? It is a piece of data which also has methods that can operate on it. In the case of an image, you'll be able to examine and modify its pixels with these methods, which you will learn about soon. Next is the name of the type to create. Here, you want to make a simple image, which is part of the Duke Learn to Program libraries and gives you a simple way of working with images to get started. Finally, there are parameters in parentheses. These parameters specify more information about how we want the object created. In the case of simple image, we can pass in a string which names the image file that we want it to load. This parameter is what tells the first line to load drewrobert.png and the second line to load dinos.png. There's a lot more to learn about objects and constructing them. You'll learn a little bit more about using objects shortly. However, we won't go into too much detail about how to define your own types or objects, called classes, until later courses. We'll talk a bit more about construction in later courses too, although if you want much more detail on that topic, you would also want to take the follow-on specialization from our friends at UCSD. Okay, great. So now you know about variables, which are boxes that hold values, and how to declare and initialize them, as well as how to update them with assignment statements. You've learned that expressions are combinations of values, such as variables and constants, as well as operations such as plus, minus, and times. And you learned about new simple image, which lets you create a new image by loading the contents of an existing image file. These are the first pieces you need to understand to be ready to turn the green screen algorithm into code.
Okay, so now you know about variables, but you also need to know how to do things like look at particular pixels and change their colors. How could you do these things? The answer is that you can call some methods that are built into simple image, which already have the code to perform these operations. In general, methods let you perform some operation, possibly one that is quite complex, on an object. Here is an example of calling two methods, getWidth and getHeight, to get the width and height of an image respectively. Let's break down the syntax. First is the name of the object we want to invoke the method on. Which simple image's height do we want to get? Whatever simple image we name here. Next is a dot. The dot operator means inside of. We want the getHeight method inside of FGImage. Next is the name of the method that we want to call. In this case, it is getHeight. Finally, there are parentheses. Parentheses after a name indicate that it is a method or a function which is similar. If the method took any parameters, you would specify them inside the parentheses. Now that you have seen the syntax of a method call, let us see the semantics. Before we step through the behavior, we'll describe the semantics. First, execution goes into the method. You stop executing statements where you were, go inside the code for the method, and then do whatever code is there. You do that code by following all the normal rules for executing code. It has the same semantics whether it is inside a method or not. At some point, the method will figure out what answer it wants to give back, which is called returning its answer. The method call, which is actually an expression, evaluates to whatever value the body returned. Then you continue executing code after the method call. Let's see those rules in action. The first line we have seen before. It makes an image and initializes FGImage to refer to it. Next is a call to FGImage.getWidth. The code for getWidth is in the Duke Learn to Program library. We don't actually know what the code is, but that is fine as long as we know what it does. The computer would then go into that code and start executing it. That code would figure out what the width of FGImage is, that it's 480 pixels, and decide that 480 is its answer. Since this method's answer is 480, the call FGImage.getHeight evaluates to 480. Another way to think of that is that it's like a mathematical operation with the result 480. Now execution comes back to where it was, which is halfway through this assignment statement. We finished the assignment statement by making a box for W and putting 480 in it. Now a similar process happens for the call to FGImage.getHeight. The computer executes the code inside the Duke Learn to Program library, figures out that the answer is 270, and returns that value to where the method was called. Execution then returns to where the method was called. And the assignment statement finishes as usual. So how do you know what a method does? Well, if you have the code, you could see what it does, stepping through it line by line, following the semantics of the code. But what if you don't have the code, as in this case? You should read the documentation, a written description of what a method does. For simple image, you can find documentation about it on DukeLearnToProgram.com. If you were to go to the DukeLearnToProgram.com website, you would see a link for documentation. If you clicked on it and looked at the left, you would find a list of the topics that are documented. One of these is simple image. If you click on that, you would get to a page that lists the various methods in simple image, including getHeight. If you were to look at this entry, you would see that it describes the behavior of the method. It gives you the height of the image in pixels. We have said that methods are invoked on an object, but what exactly does that mean? Well, if you are asking for the height of an image, which image's height do you want? The answer is whichever image you invoke the method on. To see this in action, let us look at this example, which has two images. Our first line of code makes one image called FGImage, and our second line of code makes the other image called DImage. Now we are about to do FGImage.getWidth. Since we are invoking the getWidth method on FGImage, it's going to work with the image referred to by FGImage and give us its height. Execution jumps into the getWidth method in the DukeLearnToProgram.com library and does whatever the code there says to. Notice that the method looked at FGImage and found its width, coming up with an answer of 480. The method call evaluates to 480 and the assignment executes as you have learned. Now the next line is dimage.getWidth. Since this method is being invoked on dimage, the method will operate on the image that it refers to. Again, the execution jumps into the DukeLearnToProgram.com library's code and does whatever the code there says to do. However, this time it is working with a different image. So it comes up with a different answer, 140, which is what this method call evaluates to. Finally, we return to the method call and finish the assignment statement. Some methods have parameters. For example, if you wanted to call getPixel on an image, which gives you a particular pixel, it might look like this. Notice that we have 0, 0 in the parentheses. What do these mean? These are the parameters to the method. They give the method more specific information about what it's supposed to do. In the particular case of getPixel, the parameters specify which pixel it should get from the image by giving the desired pixels x and y coordinates. The particular meaning of the parameters is specific to each method, but should be described in the documentation. Methods combine together multiple potentially complex steps that operate on a specific object. There's a similar concept which does not work on an object called a function, which we will discuss next. Thank you. Methods combine together multiple potentially complex steps that operate on a specific object. There's a similar concept which does not work on an object called a function. For example, printx is a call to the print function passing in x. Printx will print out whatever x is. This is a function as it does not belong to any particular object. Notice there is no object dot before the word print, but the syntax is otherwise the same. You can write your own functions, which can be quite useful to avoid duplicating code and to make testing and debugging easier. You could write your own methods too, but we are not going to talk about writing classes and methods in this course. We will, however, discuss them in Java in the later courses. To see an example of writing your own function, let us take a look at this relatively simple example. A function that takes a number and squares it. We have defined the function first and then called it later. Now let's break down the syntax, then see the semantics. First, we have the keyword function, which says that we are about to define a new function. Then we have the name of the function. As with variables, you can pick most any name you want, but it should be descriptive. In this case, square is a good name, since it describes what the function does. Squares a number. Next, we have the parameter, list in parentheses. Here we are declaring the names of the parameters. These will act like variables, which are initialized by the values passed in when the function is called. They tell the function what specifically it should do. In this case, the parameter says what particular number to square. We decided to call it x. If there were multiple parameters, we could separate their names by commas. Next is the body of the function. This is the code that specifies what the function should do. The body of the function is always inside of curly braces. There's a new type of statement in the body of this function. Return ANS semicolon. This is a return statement, which is how a function says what its answer is. The syntax of a return statement is the keyword return, followed by an expression whose value is what the function should give back as its answer, followed by a semicolon. Later in the code, we have a call to this function, which is how we make use of it. Here we are squaring 4 and using the result of that computation to initialize the variable y. Now that you have seen the syntax of declaring and calling a function, let's step through the behavior. The declaration itself is not executed. It just tells the computer what the function means for later use. So we start here, right before the variable declaration. The first thing that we need to do when we call a function is create a frame for it. This is a space for the function to have its own parameters and variables. As you will see soon, they go away when the function is done. Next, we need to make a box for each parameter that Square expects. In this case, Square expects one parameter called x. So we're going to create one box named x. We will initialize the x parameter with the value 4, since that is what was passed into the function call. Next, we're going to make a note of where we called Square from. We note it with a 1 in the top corner of the frame, and in the code on top of the call. This may seem trivial in this example, but if the Square function were more complicated and called in many places, we might forget where to come back to. Now that the frame is set up, we jump into the code for Square. Our execution arrow moves into the body right before the first line of code. Now we begin executing the code, here according to all the normal rules. We make a box for A and S, and initialize it to 4 times 4, which is 16. Now we are right before a return statement. Return statements are a new concept, but they tell the computer to give an answer back from this function. In this case, the answer to give back is 16, since we are returning A and S, and the value of A and S is 16. This means that the call to Square that we are executing will evaluate to 16. Now our execution returns where we made the call, and we finish the assignment statement normally. Okay, great. Now you know how to call methods and functions, as well as the basics of how to write your own function. But why are these so important? Well, they are a great example of abstraction. They package up a computation which may be quite complicated, or which may require knowing details that you should not need to be concerned with, and give that computation a simple interface. For example, the interface of the simple image method getWidth is that you call it on an image, and it gives you the image's width. The implementation is hidden in the DukeLearnToProgram.com libraries, and you've not seen it all, nor do you need to see it to use it. Thank you. Welcome back. Now you've seen a bit of code that works with images and numbers, 2 different types of data. But what if we do something that does not make sense, like try to do w.getWidth? W is the number 480, which doesn't have a getWidth method. In this particular case, the code will crash when execution reaches this line. So why is this call to getWidth fine? But this one crashes the program. If we go back to our diagram that depicts the state of the program, you will see that we were working with 2 different types of data. FGImage refers to a simple image, which has a getWidth method. But W is a number, a type of data that does not have a getWidth method. So what exactly is a type? Well, remember that everything is a number, but we have lots of different things we want those numbers to represent. Letters, images, sounds, and just plain numbers. So the type tells us what those numbers mean, that is, what kind of thing the number represents. This is important because the type specifies not only how the program should interpret the number, that is, what the numeric value means, but also how to operate on it. The same operation may have different behavior on different types. This may sound confusing, so let's look at an example. Here we have some code, which has 2 plus operations in it. As you are about to see, these 2 pluses will do different things since they will operate on different types of data. Let's step through the code. N1 equals 26. N2 equals 16. S1 equals open quotes A, close quotes. Here, S1 is a string, a sequence of letters. This particular sequence has just one letter, A. S2 equals open quotes B, close quotes. Now we're about to do the first plus operation. Here we are doing N1, which is 26, plus N2, which is 16. Both operands are numbers, so we are just doing numeric addition. 26 plus 16 is 42. Now we are about to do the second plus operation. However, here we're doing plus on two strings, A and B. What does it mean to do plus on strings? For strings, plus does not mean numeric addition, it means concatenation. Concatenation is a fancy word for taking two strings and sticking them together one after the other. So you get S3 equals the string AB. Notice how plus meant two different things based on the type of the data it was operating on. So how does JavaScript keep track of the type of the data? It keeps information about the type explicitly along with each value when it stores it in the computer's memory. Then whatever it needs to work with a value, it reads the type and value out of the memory to figure out what to do. Because JavaScript keeps the types of all values in memory, meaning that it tracks and works with the types while it runs the program, it's called a dynamically typed language. If you stay for course 2 and beyond, in which you will learn Java, types will work differently. Java is a statically typed language, which means that every variable and every expression has exactly one type, which must be known before the program can even be run. For this to work in Java, you, the programmer, write down the types of your variables explicitly in your code. Then your code can be checked for certain kinds of mistakes, like trying to call getWidth on a number, before it is even run. Having this kind of mistake found before the program runs is really helpful. You'll learn more about types and Java in course 2. For now, however, we have a bit more JavaScript to do so that you can implement the green screen algorithm. Thank you.
Now that you're learning a bit about JavaScript, you might wonder where you would write it, or how you would run it. In CodePen, you can write JavaScript in the right frame, which we have highlighted here. If you use some other tool to write a web page, you can generally write JavaScript code in your web page easily, though the specifics will depend on the tool. However, for getting you started, we have a slightly more novice-friendly environment, which we hope will help you write and debug your code more easily. If you want to write JavaScript for a web page somewhere else, you can always use this environment to develop your code, then copy it into your web page later. Here you can see a screenshot of the DukeLearnToProgram.com web environment for developing JavaScript code. This is a page for the green screen algorithm, where the box to write code is on the left, is preloaded with the algorithm that we have developed together in a previous video. If you click on this button at the bottom, it will run this code. Here the code is not finished, so not much would happen. But if you were to finish this code, as we will do soon, the output would show up on the right here. In fact, if we had finished this code before we hit the run code, you'd see Drew and Robert appear with their dinosaurs. Okay, so why use DukeLearnToProgram.com rather than just writing your code in CodePen? For one, we have set up the Duke Learn to Program environment to give you more friendly error messages. This will make it easier to fix syntax errors in your code or to find and fix problems. We have also set it up so that you can print a variety of things, such as simple images and simple pixels. These make it easier to see your output and can also help you debug. Speaking of simple image and simple pixel, these are not standard JavaScript libraries. Instead, they're libraries that we have set up for you so that you can solve interesting problems earlier in your learning. These libraries make it easier to manipulate images without a bunch of nitty-gritty JavaScript knowledge. Of course, if you want to use them for your web pages that you make elsewhere, you could import the libraries and use them in any web page you build. For this course, later we'll look at how to use them in CodePen. These pages are also set up to be preloaded with images and pseudocode for the problems that you can work on, so that you have a good point to get started from. Lastly, most programmers use environments like this to make the tasks of programming easier, whether it is CodePen, BlueJ, which we'll introduce when you learn Java in the next course, or DukeLearnToProgram.com. All right, let's see it in action. Welcome to the Duke Learn to Program environment. This is what we've created for you to help you learn to do your JavaScript programming. And we've done that because we believe that it provides a better environment. So let's start writing some code and playing with it and just sort of seeing what happens. The first thing I'm going to do is simply create a variable, name it x, and give it an initial value. And then I'm going to create another variable, and I'm going to give that a value as well that's dependent upon x. And now I want to see the result of that computation, see if I've actually done something that is going to be what I expect, and so I can print out the value of y. And when I run it, when I press the Run Code button down here, I see the results over here in the See It window. So the result of 3 times 3 is going to be 9, which is just like what we'd expect. Let's do something a little bit more complicated. Let's write our own function. So that starts with the function keyword, and then we can give it whatever name we want. I'm going to write a very small function that simply squares whatever value is passed in. So I'm going to say the square of x is what happens when you multiply x by itself, and you get that result. You'll notice that when I put in that initial brace, that it put one in for me, kind of filling that out. That's, again, an attempt to help you by filling in that stuff. And you'll also notice here that the fact that I use the variable name x doesn't have anything to do with this variable name x up here. This is just a generic name that I've chosen to refer to any value that you pass in when you call square. So now let's try actually using that, and we'll go ahead and make a new assignment to y, and we'll say, oh, we want y to be the square, the result of calling square of 5, say. So now when I run that and I want to see what the result of that is, so I'm going to print out y again, and I run that code, you'll see that the first print is still called, so those lines are executed, and I get the result of that, and that's 9. Then I define my function, and then I call that function with the value of 5. That multiplies 5 by 5 and assigns that value to y, and I print that value out, and I get 25. So both of the print statements occurred, and I get to see their results. I can also print out the result of calling a function directly if I want. I don't have to assign it to a value. If I just want to see that, I can say print the square of 4, and again you'll see that it filled in those parentheses for me, and I want to put a semicolon at the end of the line to mark that I'm done with that line, and I say run code, and again all of my print statements are executed in the order that we see in my code. So first I get 9 as before, then I get 25 as before, and now I get 16, which is the result of calling it directly. If I wanted to, I could choose not to execute any of these prints, and typically a way to do that, if I'm not quite ready to get rid of the code, is I can go ahead and I can put a comment in front of it. I can put those 2 slashes, and again you'll notice that the environment color codes that, just like you saw in the CodePen environment, this is a common feature of most development environments, and so it's made that a green color to indicate that that's a comment. Typically, you would use comments like the one on our first line here that's used to kind of describe your code or explain what's going on, but you can also use it to just comment out a piece of code to say, I'm not ready to have this execute during this run of the program. And so you'll see now I just get the 2 print statements, the 9 and the 16. Okay, let's try one more thing. Let's go ahead and make a variable that represents an image. So if I create a new simple image, then I can go ahead and print out the result of that. But what value should I use to initialize my simple image with? Well, in our environment, we've provided you with a number of standard images that are already uploaded and ready to go. And different problems may have different sets of images that are associated with them. So in this particular case, we can see that we have the very first image here is chapel.png. So if I just put that string in there, chapel.png, then that will refer to this image down here that's already been loaded. I can go ahead then and say print my image, and when I run that code, you'll see that I still get the first two, the 9 and the 16. Those prints are still being executed, and then I also get an image printed out over there, which is the image that I loaded in. And I can go ahead and change that if I want. So over here is, on the other end, is an image of Professor Roger. So I'm going to go ahead and put Roger in there instead of Chapel, and when I run that code, I get a different image. If you want to, you can also drag your own images over. So here I have some images, and I can go ahead and drag the image down into that space, and you can see that it loaded brownhorse.jpg, and it also includes the size of that image so that I can do calculations based on that or check to see if I've got things correctly. So I'm going to go ahead and change this to brownhorse.jpg, and in addition to printing out the image, I'm going to print the width of that image. And when I run that code, you can see that I got 1280 as the width, which was noted down here. And you can see that I got a very, very big image that is taking up a lot of space over in the see it area. But I can see that image if I want. I do want to take a moment to assure you that anything that you upload to your browser to display as images to work with are going to stay on your local machine. So all of this work that's happening through this environment is happening on your local machine in your local browser. Nothing's being sent to Coursera, nothing's being sent to Duke, nothing's being sent off of your computer because you're doing that. In order to make sure you don't lose your code when you're using your web browser, if you try to go to a different page and you haven't yet saved your code, you'll get a dialog box that says, hey, are you sure you want to do that? And so you can go ahead and say, I'd like to stay on this page, and then save the code to your computer to make sure that you have a version of it that you're comfortable with. And now I can go ahead and leave the page because I have a saved version of it. Now that you've seen some of the basics of JavaScript and have seen the Duke Learn to Program environment, you still have a few pieces to learn in order to be able to implement the green screen algorithm. One of those pieces is repeating some steps of the algorithm, doing them once for each pixel. Repeating steps is incredibly common in algorithms. As you program more, you will find that most algorithms you write have some form of repetition. So how do you write repetition down in JavaScript? You use a loop. In this case, you would use a for loop, which will repeat some steps for each pixel. You can see an example of a for loop here. Although the steps inside of it are not the ones for the green screen algorithm, you still have a few things left to learn before you can do that. Let's start by breaking down the syntax of this loop. First, you have the keyword for, which says you are writing a for loop. Next, you have information about how to do the repetition inside of the parentheses. The first part of this information is the variable declaration, here var pixel, which makes a new variable to refer to the current item. The loop will automatically update this variable each time it repeats, setting its value to the next piece of data. In the case of this loop, each piece of data will be a pixel. Next is the keyword of, which says that you are about to say what pieces of data to iterate over. Then you have the expression that evaluates the data you want to iterate over. In this case, we have image.values. The .values method inside of simple image gives back all of its pixels to access each one in turn within the loop body via the variable pixel. Finally, you have the body of the loop inside of curly braces. The body of the loop is the set of statements that should be repeated for each piece of data. Okay, great. Now that you have the basics of the for loop syntax, let's look at the semantics. Here we are about to begin execution of the for loop. We are assuming that the variable img was previously declared and initialized to refer to this 2x2 image. We've drawn a light blue box around the image and made the arrow in img's box match this color to help make it clear what the arrow is referring to once we start drawing other arrows. IMG's arrow refers to the image as a whole. The first part of the for loop creates a new variable named pixel, so we are going to create a box for that variable. The second part says that we are going to do a loop over each pixel in the image. So we will start with the pixel variable referring to the first pixel in the image. Notice that the arrow is pointing at one particular pixel. It is also important to note that we are referring to an existing pixel inside of the image, not making a new pixel. Why does this matter? In a moment we are going to change the color of the pixel, and the change will show up in the image, since var pixel is the actual pixel inside that image. This box on the right lets you peek inside of the pixel's numerical data. The pixel has X and Y coordinates and red, green, and blue component values. These are not separate data, but we write them here so that they are clear as we manipulate the pixel, since they don't show up directly in the conceptual colored squares picture. Now we go inside the body of the loop and begin executing statements there. The first statement declares a variable called new g and initializes it to 255 minus pixel.getGreen. If you look at the numerical data for this pixel, you will see that its green value is 0, so new g will be initialized to 255. Next, you are going to do pixel.setGreen to new g. Since new g is 255, this will set the pixel's green value to 255, changing its color from magenta to white. Now, the next thing in the code is the close curly braces, which ends the body of the for loop. Whenever you reach the end of the for loop's body, you go back to the top of the loop and move to the next piece of data. In the case of this loop, that means updating the pixel variable to the next pixel in the image, like this. Now you are going to do the steps in the for loop again with the next piece of data. Or as a programmer would say, you are ready to do the next iteration of the loop. We start by going inside the body of the loop and executing the statements there again. Again, we declare and initialize new g to be 255, and then do pixel.setGreen to 255, and that changes the second pixel from blue to cyan. Again, we are at the end of the loop, so it is time to go back up to the start of the loop and update the pixel to refer to the next pixel in the image. Again, we go into the body of the loop and declare and initialize new g. This time, however, since the green value is 255, the value of new g is 0. We do pixel.setGreen to 0, which will change this pixel from green to black. We once again find ourselves at the end of the loop. Can you guess what happens next? We go back to the top of the loop, updating the pixel to refer to the last pixel in the image. We go into the loop body, declare and initialize new g, and then do pixel.setGreen to 0, which changes this last pixel from white to magenta. And once again, we are at the end of the loop. Now, there is not another pixel. So when we go back to the top of the loop, there is no pixel left. At this point, the loop has nothing else to iterate over, so we jump down past the end of the loop body and continue executing whatever code might be there.
Welcome back. Now that you know how to repeat steps with a for loop, the only piece remaining to implement the green screen algorithm is to be able to make decisions based on a condition. In this algorithm, we want it to look at a pixel, see if it's green, and then do different steps based on whether it was or was not green. Now let's learn how to implement decision making. Decision making is done with if-else statements. Here you see an if-else statement which looks at the condition is x less than y, and then decides which set of statements to do based on whether that is true or false. This example assumes that the variables are declared and initialized previously. Let's break down the syntax. First, you have the keyword if, which tells JavaScript that you are writing an if-else statement. Next, you have the condition to make a decision based on, here it is x less than y. This condition is an expression written inside of parentheses. After the conditional expression, you have the then clause. The then clause is the set of statements to execute if the condition is true. These are written inside of curly braces. After the then clause is the keyword else. Then the else clause. The else clause is a set of statements to execute if the condition is false. Again, these are written in curly braces. Sometimes you may see an if statement with no else clause, in which case both the keyword else and the else clause are omitted. This is shorthand for an empty else clause, whenever the programmer does not want to do anything in the case of a false condition. Okay, now that you have the basic syntax, let's look at the semantics. Here we have just reached this if statement, with our variables having the values shown on the right. The first thing that happens is we evaluate the conditional expression, is x less than y? To evaluate this, we look at the values of these variables, the values they have in their boxes, and see that we are checking if 2 is less than 7. 2 is less than 7, so this expression evaluates to true. Since the condition is true, we go inside the then clause and begin executing statements there. We execute the statements here according to their normal rules. This next statement is an assignment statement, z equals 2. So we update z's box to have 2. Now we are at the closed curly brace of the then clause. We are done with the statements here and need to skip over the else clause since those statements are only for when the condition is false. So we jump down past the end of the else clause. We would then keep executing whatever code comes next. Now let's look at the example again, but with different values for our variables. We again begin by evaluating the condition expression, is x less than y? However, this time, x is 42 and y is 7. So we're evaluating, is 42 less than 7? This expression evaluates to false, since 42 is not less than 7. Since the conditional expression evaluated to false, we jump into the else clause and begin executing statements there. Again, we execute statements according to their normal rules. First, a equals y plus 1, which updates a to be 8. Then y equals x minus 3, which updates y to be 39. Now we are at the end of the else clause. So you can just go past the closed curly brace of the else clause and begin executing whatever code comes next. You have seen several important concepts separately, but it is instructive to see them all put together as in this example. One important thing to remember when putting pieces together is that they generally follow the same rules, no matter how they are combined. A concept called compositionality. Let's see what this code does. First, we declare a variable called img and initialize it to a new simple image, which is the 2x2 image you saw in previous examples. Next, there is a for loop, which iterates over each pixel in img.values. You've already seen how this works. And we will again follow the same rules. We create a box for the pixel variable, initialize it to the first pixel in our image, and go into the body of the loop. Now we have an if statement. It does not matter what this if statement is inside a for loop, it still follows the same rules. Is 0 greater than or equal to 2 divided by 2? No, that is false. So we go into the else clause and execute statements there. This will set the pixel's blue to the pixel's red value, which is 255, changing it from red to magenta. Now we're at the end of the else clause. So we go outside of it, which brings us to the closed curly brace of the for loop. So we go to the next pixel and back to the top of the loop. We again go into the loop body, but now the pixel's x is 1. So we're asking, is 1 greater than or equal to 2 divided by 2? That's true. So we go into the then clause and execute the statements there. Pixel.getRed divided by 2 is 0 divided by 2, which is 0. So we set the pixel's red to 0, which does not change anything since it was already 0. We are now at the end of the then clause. So we jump just past the closed curly brace of the else clause. We have again reached the end of the for loop, so we go to the next pixel and jump back to the top. This pixel's x is 0, so we are again evaluating, is 0 greater than or equal to 2 divided by 2, which is false, so we go into the else clause. We execute that statement and leave the else clause and go to the next pixel as we jump back to the top of the loop. Going back into the loop for the last pixel, we evaluate the condition, which is true, so we enter the then clause. We are going to set the red to 127.5, but pixel set red will round that to 127, since the pixel only works with integer RGB values. Now the pixel is light cyan instead of white. We have reached the end of the then clause, so we jump past the end of the else clause, which brings us to the end of the for loop. We go back to the top, and there's no more pixels, so we jump past the end of the loop and begin executing whatever code might be there. Thank you.
Okay, now it's time to turn our pseudocode into JavaScript code. For this video, we've already started by filling in some of the code because it is so much like our previous examples, and we figured that you've seen it before, so we don't need to go over it again. So that's creating the FG image, the BG image, and the output image that is the same size as the FG image. So we're going to get down to actually writing the code, which says to process each pixel in the FG image. So we've written our standard for loop that goes through each pixel of FGImage.values. So now we're at the first line of pseudocode that is non-standard, that's specific to this problem that we haven't written before. And that is to look at the current pixel and determine if it's green. It turns out that we didn't really figure out what green is in our planning. So we have to kind of figure that out now as we're coding. We intuitively understood it when we were working out our plan, but how do we explain it to a computer? How does a computer know what green is? Right now we're not sure, so we're going to start very simply. And we're just going to say if the green component of the current pixel equals 255. That's an example that we've seen before that we understand means that something has a lot of green in it. In fact, it means it has all the green in it. And so that's a simple place to start, and we'll see how it works out as we go. Starting simply is often a good strategy for when you're writing code, just to make sure that we have something that works. With that done, let's start looking at what we're going to write when that condition is true. And then we're going to go inside the conditional and write that code. So it says to look at the same position in the BG image. And we recall that every pixel has a coordinate location within an image given by its x and y values. So we're going to go ahead and get those and store them in variables named x and y reasonably. So that is the corresponding location in the FG image, and now we want to get the pixel of the BG image at that same spot. So we'll call get pixel with x and y to get that value. So now those three lines represent that one line of our pseudocode. So we needed to do a little bit of work to translate that one line into actual code. Now that we have the corresponding pixel in the BG image, we want to set that to the corresponding position in the output image. So we're going to do that by calling set pixel with that x and y and the BG pixel that we just got. And that completes the inside of that if statement. Okay, let's look at our last line of pseudocode. It starts with the word otherwise. Well, what does otherwise mean? Otherwise means only do this last piece if the condition on line 12 was false. Well, how do we write that code? Well, we could write the opposite or the negative of the condition on line 12, but that can be hard, and so that is error prone. That can lead to problems. So most languages, including JavaScript, include something called an else statement, a shorthand for this situation. An else just means if the condition above on line 12 was false, then run this code instead. So what do we do when we say otherwise? We're going to set the output's corresponding pixel to the current pixel. So we're going to say output dot set pixel x and y again, but in this case we want the current pixel, so that's just pixel. Now we wrote x and y here, and those might be, and those are things that we want to compute just like we did before, and I'm just going to show you a different way to do it than how we did before. I'm going to write these values in line, whereas in the previous version I wrote them and stored them in a variable. So from a functionality perspective of the code, these work exactly the same. Whether I decide to save it into an instance variable or whether I pass it directly into the function doesn't matter from the programming functionality perspective. So you should use the one that you're most comfortable with. Some people find it more readable to give every value a name, and some people find it more readable if the code is a little bit shorter and they can write them in line. It's entirely up to you what you want to do. But now I'm going to review my pseudocode and see that I start out and I've got for each pixel. That was my standard loop. I'm checking to see if the current pixel is green. Then I'm getting the pixel at the corresponding x and y coordinates in the BG image. I'm setting those to the corresponding position in the output image. If that wasn't the case, then I'm setting the pixel, the corresponding pixel in the output image to the foreground images or the current pixel. So I feel pretty confident at this point that my pseudocode is correct, or that my code corresponding to my pseudocode is correct. So I'm going to run the code. It doesn't work. Oh my goodness. I just double checked it and I have exactly what looks like the foreground image. This doesn't look like it applied anything at all from the background image. How could that possibly be? Well, if you'll recall, when we were starting this video, we sort of felt like our idea of what green was a little bit hazy. And this is a very exact measure for what green is. This is saying that green has to be exactly the maximum value of green, which is 255. So I'm going to try to have a more loose definition of what green is, and I'm going to try, say, 240 as a value. So this now gives me a variety of green values to work with, and let's see what happens when I run this code. Ah, that looks a whole lot better. Now I can see dinosaurs, now I can see space. It seems like it worked a whole lot better to give us this range. However, if you look very closely at the image, you'll see that Drew and I have a halo around us. We have a green halo where we weren't quite correct in our range. So let's try, since that worked so well, let's try upping the range a little bit more and say making it 200. So that gives us even more green values to work with to try to get that halo to go away. And I ran the code again, and now you can see that the colors, the space colors, are bleeding into Drew's shirt, and so it looks like Drew is fading into space, and that's not what we want either. Now we could spend some time trying to perfect this range for this particular image so that we get the halo to go away, but space doesn't intrude on the foreground image. But that doesn't seem like the best way to go about solving this problem, because we're really just going to make it work for these two images for this particular range of colors. So let's think about a different way to define green that might be a little bit more general and robust. So instead, I'm going to define green as a color that has more green in it than both red and blue combined. So I'm going to write that as green, the value of green is greater than the value of the red and the blue added together combined. So now when I run the code, I see that the halos went away and the space went back to its proper place. So I'm very happy with the results of this code that I've written. I've gotten my code to work for these two images, and I feel very good about it. But to be certain of my code, I would certainly want to try it on a wider variety of images to see if I've really defined green correctly and gotten it to work. But I'm going to leave that as an exercise for you to encourage you to experiment on your own with your own images. Now you're going to think about what it would take to turn the blue devil into a green devil, for example, to celebrate an environmental initiative on campus. What code would go inside the for loop to make the devil green? Specifically, we want to end up with a background still being white and the foreground having a 0 for red, a 255 for green, and a 100 for blue. Take a few moments to think about how to do this. A first thought might be code that looks like this. Here we set the red, green, and blue components of each pixel directly to the values we want. However, as the loop goes through each and every pixel, it turned them all green. If instead you only set the green of each pixel to 255 and the blue to 100, you get an image that looks like this. This code made the foreground the right color, but now we have a yellow background. Take a few moments to think about why this happened. Did you realize that the background is yellow because it has a red value of 255, making the overall color value of the background red 255, green 255, blue 100? Because we did not change its red value, it kept the original one. And since the background was originally white, that value is 255. To make this work, we're going to need code that makes a decision using a conditional statement like we've seen before, so that it can change the foreground but not the background. Here is one possible idea for an if statement. If the blue is 255. This seems like a logical choice because the foreground is blue and we want to change only the blue pixels to green pixels. Take a moment to think about what this code does. Do you think it will accomplish what we want it to? This code actually turned the background green, but left the foreground blue. That behavior is the opposite of what we wanted. Doesn't that seem surprising? It is important to remember that the computer only does what you tell it to. Anytime your program does seem to behave oddly, there is a good reason behind it. We're going to take a closer look to understand what happened. The white pixels in the image have 255 for red, 255 for green, and 255 for blue. Because each white pixel has blue equal to 255, those pixels are set to green by this piece of code. However, the blue pixels in this image are not pure blue. They have 45 for red, 39 for green, and 225, not 255, for blue. Accordingly, the condition is not true for the blue pixels, and they are left unchanged. To fix this program, you would need a condition that distinguishes the foreground pixels, 45 red, 39 green, 225 blue, from the background pixels, 255 red, 255 green, 255 blue. There are many possible conditions we could write. You could check if red is less than 200, if green is 150, if blue is equal to 255, or many other possibilities. Here, we made one such change. We changed the code to check if red is less than 200. This code produced a green blue devil image that we wanted. Whenever your code does not do what you want, thinking about why it is behaving a particular way is an important part of fixing it. We'll talk more about debugging code soon, and teach you how to apply a version of the scientific method to fix problematic code. We'll also teach you how to invest some planning time at the start of the programming task so that you can write better code the first time and spend less time fixing it at the end.
In the previous lesson, we learned about the 7-step process to write a program. The 7th step was to debug failed test cases. In this lesson, we're going to talk more about step 7, debugging failed test cases. In particular, how would you go about doing this? This is an important step of the programming process because you aren't typically going to write your program correctly the first time. Everyone makes mistakes, and it's easy to have small problems that cause your program to work incorrectly. We need a good way to do this, and we're going to use the scientific method. Now, you may or may not remember the scientific method from elementary or middle school, or you may have learned it a little bit differently, so we're going to review it here. The first step is that you observe a phenomenon. In the case of your program, this is generally that it crashes or exhibits some incorrect behavior when you test it. The next step in the scientific method is to ask a question. In other fields of science, this might be something like, why does an apple fall to the ground, or why do these birds have slightly different beaks? In programming, it's generally, why is my program broken, and how is my program broken so that I can fix it? The next step is to gather information and apply expert knowledge. You may think you want to jump straight to forming a hypothesis, but forming a good hypothesis is often very difficult. If you were Newton, you might not just figure out the theory of gravitation from seeing one apple fall. You might have to go do many experiments with many different apples or other objects to come up with the equations of physics that he discovered. For programming, we're going to gather information about the inner workings of our program. We may need to do multiple experiments to see what's happening inside of there. We're also going to apply expert knowledge. This is the knowledge of the particular field in question, in this case programming, to help us think about the data that we gather, analyze it, and understand what's wrong. This step is an iterative process. As you gather information, you're going to realize other information you want to gather and other things you want to think about. You keep doing this step until you're ready to form a hypothesis. When you form a hypothesis, you're going to make some statement which predicts behavior about your program. I think that when my program does this, the following happens. Once you've formed a hypothesis, you're ready to test it. You're going to conduct some experiments to either reject the hypothesis if the behavior of your program contradicts it, in which case you're going to return back to gathering more information and applying your expert knowledge again. At this point, you've learned something new from the fact that your hypothesis was incorrect, so you have more knowledge to work from and are ready to form a better hypothesis. The alternative is we could become convinced that our hypothesis is correct because all of the evidence agrees with it, in which case we accept our hypothesis, we understand what's wrong with our program, and we're ready to act on it and fix our program. To dive a little more deeply into the gathering information step, since this is one of the most time-consuming steps of the process, how do we actually go about this? Well, we need to look at the inner workings of our program to see what's going on inside of everything that it's doing. We could add statements that print things out, print the values of variables, print when we reach certain lines of code, or any other information we might find useful in this process. We may also use debugging tools. There are specific programs written to help people debug their programs. They let you step through the execution line by line, inspect the value of variables, even change the value of variables, or watch to see when variables will change. What particular tools are available depend on the language that you're working in, but mastering these tools can be incredibly powerful and helpful. In some cases, you may also find it instructive to execute your code by hand, stepping through it line by line, writing down the effects of each line, and figuring out what's going on, which will let you see exactly what's happening in your program, which may lead you to some insights into its behavior. As you do all of this, you're going to apply expert knowledge. You're going to gain more expert knowledge with experience as you become a more experienced programmer and debugger. things will come more naturally to you because you'll have seen similar situations, you'll recognize what certain symptoms of a program mean, and you'll be able to debug with more ease. Speaking of our hypotheses, we'd like to talk a little bit more about those. What makes a good hypothesis? Well, it should be testable. That is, we should make a specific prediction about the behavior of our program, something that we can either refute if the program's behavior does not match that prediction, or something that we can become convinced is the case. It should also be actionable. That is, something where once we've convinced ourselves that it's true, we can go fix our program because we now know what's wrong with it. Being specific as possible in forming our hypothesis helps with both of these aspects. Let's see a couple examples. First, we're going to start with an example of a very poor hypothesis, which provides us no useful information. My hypothesis is, my program is broken. While this may be true, and in fact likely is if we've observed a failed test case, this does not tell us anything useful about how to fix our program. A slightly better hypothesis would be, the problem is on line 5. This tells us a little bit about where something is wrong in our code. We might be able to act on it in some ways. We could go look at line 5 and see what we can figure out is wrong, but it doesn't really tell us what's wrong. An even better hypothesis would be that the problem is division by 0 on line 5 of our program. This tells us specifically what's wrong and where it's wrong. We could test this and see if we're dividing by 0, and we might be able to act on it. But we can do even better. Here we have a very good hypothesis. The problem is division by 0 on line 5, specifically for inputs that meet certain criteria. In this example, maybe red is less than 30 and green is greater than 245. So this hypothesis is testable. We can go and craft specific inputs that tell us whether it's exactly these criteria and exactly this behavior, and it's very actionable. Once we've convinced ourselves this hypothesis is true, we know exactly what to do to fix our program. We go back to steps 1, 2, and 3 of the 7-step process, and we see what's special about these particular class of inputs and how they need to fit into our algorithm as special cases, adapt our algorithm, and then fix our code. When we want to test our hypothesis, the way we're going to do this is we're going to run our program. We'll take whatever test cases we find appropriate, use them as inputs to our program, and run it and see what happens. If the program's behavior matches our prediction or not is going to be the outcome of the test case. If it does not match the behavior, we're going to reject the hypothesis. Anytime we get contradictory information, it indicates our hypothesis was not correct, and we need to go make a new hypothesis. If it is the same behavior that we predicted, then we're not ready to accept our hypothesis immediately. We just become slightly more confident in our hypothesis, and we continue testing until we become confident enough that we're ready to accept our hypothesis. Checking our hypothesis is very similar to gathering information. We could potentially just run it and see the output, but sometimes we need more information. We might want to print the state of internal variables or examine other things about the behavior of the program. Now, in doing this, we've taught you a good way to debug a program. However, there's this temptation that many programmers often fall into to make ad hoc changes. Maybe if I just change this one thing, add a +1 here or a -1 there, maybe it will work. If I just tweak some code, hopefully it will fix it. I might get lucky and save some time because going through and gathering information and forming hypotheses can be kind of hard work. Well, this is tempting, but it's a really poor idea. And we'd like to make a metaphor to going to the doctor for this. So suppose you're sick and you go see your doctor. Doctor, I'm coughing and don't feel well. And so the doctor's job is to diagnose you, much in the same way that your job is to diagnose and fix your program. Does your doctor just randomly try things? Take this medicine and see what happens. If so, I would get a new doctor. No, your doctor uses the scientific method. He or she is going to gather information, running some tests, apply expert knowledge, all of the things he or she learned in medical school and has seen from experience in working on other patients, and figure out a good hypothesis, test that hypothesis, and then once he or she's convinced of what's wrong with you, take a corrective course of action based on that diagnosis. So to sum up this lesson, we've seen the scientific method and discussed it as a basis for debugging your programs. Now that you've learned some basics for creating web pages, as well as some foundational concepts for programming in JavaScript, you're ready to explore creating interactive web pages. With HTML and CSS, you've learned to create and style simple, basic web pages. With these basics and with practice, you can be creative. You can make web pages to inform, excite, and more. However, you've likely seen web pages that are interactive, that you can change in many ways. You can create an event, like clicking a button, to cause actions to happen, like uploading a file. Buttons can also change views, sort information, cause images to appear, allow you to select features in a page, and more. Connecting events, like button clicks, to responses, like causing an image to appear, is at the heart of event-driven programming. The new HTML5 standard allows for all kinds of interactivity, although you'll only explore a few features here. You'll learn the basics of simple event-driven programming with JavaScript to create interactive web pages, expanding on the knowledge of JavaScript you've built already. You'll learn how to create an interactive web page to support the green screen image processing you've done with JavaScript. By combining your knowledge of HTML, CSS, and JavaScript, you'll be able to make a new kind of web page, a web page with which you or any user can interact. The programming will be behind the scenes, with the code you write invoked by pressing buttons you create on the web page. You'll be able to click on buttons to upload images into different parts of a web page, as shown here with two images, that will be used to create a composite green screen image. Here is an example of a pen that uses buttons to allow a user to try out your green screen process. You can upload images from your computer to be the foreground and background images. You'll be able to choose images on your computer or device and upload them into the web page that you created. When you click the Create Composite button, the JavaScript code you wrote for the green screen algorithm will be called to create the composite image. With some practice and study, you could even create a progress bar to show how much of the images have been processed before creating the final composite image displayed on the web page you create. You'll learn the basics for creating a page like the one at histography.io. This website uses HTML, CSS, and JavaScript in complex ways to create an interesting, interactive web page for exploring information. You interact with the page using HTML elements and JavaScript. The buttons allow you to change how many years of information are shown, from looking at 400 years of all kinds of information to selecting only events in music over the 25 years from 1956 to 1981. To selecting a few specific events in a few specific years, such as the Beatles recording of Let It Be in the 1970s. The basics of HTML, CSS, and JavaScript will provide a great background for continuing to build your skills. Let's get to it.
We'll start learning how to use JavaScript to interact with the content on a web page by looking at simple examples of HTML and CSS, and then adding JavaScript to these simple web pages. By starting with a simple web page, you'll be able to understand how adding interactivity works. We'll start by creating a very simple web page and then adding JavaScript to it. The first version of the web page will only use HTML and CSS, with two div elements styled by CSS using class IDs. We'll introduce a new HTML element, a button, and we'll connect this button to functionality that eventually will interact with elements of the web page. Clicking the button will cause different actions determined by you, the programmer. You'll write code using JavaScript that will be able to control and interact with the web page. In the code you'll see in this lesson, you'll use a JavaScript function that executes when a button is pressed. Recall that a function is a piece of code that can perform complex steps and is not invoked on an object. We'll start with a simple example that simply alerts the user when a button is clicked. But your JavaScript code will get more complex as you learn more. And based on these simple first examples, we'll build towards an understanding of how to combine HTML, CSS, and JavaScript, as well as how to import JavaScript libraries so you won't have to write all the code yourself. you'll learn how to access different elements in a web page programmatically, using JavaScript to change text, to change color, to add new elements, and more. Hopefully, CodePen looks familiar. HTML in the left window, CSS in the middle window, and JavaScript that's currently blank on the right. There are two divs in the HTML window, with width and font size specified in the CSS window. The div with ID D1 is specified by CSS to have a background color of light blue, and the div with ID D2 is specified to have a background color of yellow. This is the simple web page we'll begin to make interactive. Let's look at how to create an HTML button and program it to have an effect when it's pressed. We'll use a new HTML tag, the input tag. It's similar to the image or IMG tag you've seen before that displays media as an image, because this tag doesn't have both a start and an end tag, but rather one tag with options within the tag. The first tag element is the type of input. In our first examples, we'll only use button as the type of input, but later we'll see that you can use color choosers as a type of input so that users can choose a color as part of interacting with a web page. And there are other types of inputs we'll see as well, including sliders, file uploaders, and more. The text displayed in the button is specified by the value element in the input tag. As you can see here, the word change will be displayed in the button. You'll also need the onClick event attribute to tell the button what to do in the case of a certain event. In this case, the user clicking the mouse. Other examples of common HTML events are when a web page is loaded, our user has moused over text or an image, or an input field is changed, for example, when you type in a password. The keyword onClick is an HTML event attribute that indicates the JavaScript that follows should react in the event of a click. This calls an event handler, which specifies what will happen when the button is pressed or clicked. In this case, the onClick event will cause an alert to be displayed. Let's see what this looks like in CodePen. As you can see, the CodePen environment pops up an alert box with a message in it. The input tag is specified that the text of the message in the onClick event handler. The user will need to dismiss the alert box before more events can be handled. Let's take a look. Here the user's clicking the button. That causes the alert box to pop up, and then the user dismisses it. But what if the alert were a more complex set of instructions? Rather than using alert directly in the input tag, we'd like to be able to use JavaScript to handle the events generated by the button. We could do this by writing a JavaScript function, which you've already done yourself. We'll call this function doChange. In the body of the function, we'll show the alert with the text click button. Then we can call the function for the onClick event. The HTML input creates the element that the user interacts with. And when the user clicks or presses the button, the event handler associated with the onClicked event, the JavaScript function, is triggered or invoked. Here, the event handler is connected to the JavaScript code by calling the doChange function we just wrote. Let's see this in CodePen. First, we write the function doChange. It has curly braces because that's what we need in a function. And then we'll copy and paste the alert code into that page. That is the JavaScript function that we just wrote. We'll change the text so that we know it's a JavaScript function that's called. So in the onClick event handler, we'll call the function doChange, but we'll edit the text in the alert box. Let's see what happens when the button is pressed. Now we can see that the event is different. This is a simple example of a good way to start. We saw how to use an HTML element to allow a user to interact with a web page. We created a button, but we'll see later that there are other types of input. We saw how to create an event handler for the event of a user clicking on the button. Because JavaScript commands can sometimes be complex, we learned how to create a function that can be called by the event handler. You'll write JavaScript in the JS or JavaScript panel in CodePen, but you'll be able to use the knowledge you gain with HTML, CSS, and JavaScript to create pages that you can deploy anywhere on the web, not just within CodePen. And you'll be able to use your knowledge of loops, variables, and if statements to interact and modify web pages. Have fun! Let's look at how to change a web page interactively using JavaScript. This interactivity will be the basis for programming a green screen algorithm in a web page and for being creative in designing your own web page. To change a page, you'll need to write JavaScript code to access elements like h1 tags or div elements or other tagged elements in the page. It's possible to access all the elements with an h1 tag, for example, or with an li tag or any other HTML tag. It's also possible to access individual elements by an ID or a group of elements by a class. We'll mostly use IDs to access HTML elements since IDs are distinct, and every element must have a distinct ID. In contrast, many elements can share the same class. In our examples, you'll see how to add a CSS class to an HTML element like a div. This will allow you to change the background color, or the width, or the height of an element. It's also possible to change the text displayed in an element, or other features. Let's look at a simple example of changing a web page using interactive JavaScript. We'll use two CSS classes, each specify a different background color for a div. By clicking a button, you'll use JavaScript to assign a CSS class to each div, making the divs change appearance and go from no background color to different background colors. The basic idea is to programmatically access each div using the IDs and change the CSS associated with the div. We'll explore this at a high level and then look at the details. Here you saw the divs change color. You may remember that each div has a different ID. One, which displays hello, has the ID D1, as you can see here. The other, which displays goodbye, has the ID D2. Recall that the onClick event attribute tells the page to create an event handler to execute the JavaScript code that follows. You'll be able to use JavaScript to access the div or whatever other element you tagged with the ID D1. That makes it possible to change the features of an element, as we'll see. In this example, the JavaScript function is called changeColor. Let's take a look at that function by looking at the JavaScript. The JavaScript function changeColor is shown here. Remember that it's called when the user clicks on the button, that is, interacts with the web page. The JavaScript function is changeColor. Remember that it's called when the user interacts with the web page, because its function is called or invoked by the onClick event handler, which calls the function changeColor. The JavaScript method getElementById is used to access an HTML element using its associated ID. You may remember that a method performs an operation on an object and is preceded by a dot. In this case, the method getElementById uses the HTML document to access its element. The label document refers to the entire HTML web page. The getElementById method has one parameter. Here it's D1, the ID label associated with a particular HTML element. The getElementById method returns this HTML element with the ID label that was passed as a parameter. That's the div element with the word hello, because the associated ID label is D1. We need to create a variable to store this returned HTML element. Here, that's shown by var dd1. Now that variable can be used to access the element and change its color. The next line creates a similar variable called dd2. This stores the HTML element returned by document.getElementById when it's passed the parameter d2. Next, to change the background colors used in this page, we need to set the background color for each div. We'll do this by setting the CSS class for the div. The line of code dd1.classNameGetsBlueback is what changes the color of the div with the ID d1. Remember, this div was stored in the variable dd1. The attribute className is one of the characteristics of an HTML element that can be accessed in JavaScript. As we'll see in later examples, There are many other attributes of HTML elements that you can also change by accessing them with JavaScript. These attributes are sometimes called fields. They're accessed using the dot notation in a JavaScript program. The code assigns the class name blueback as the class of the div stored in variable dd1. As you can see in the CSS panel of the CodePen page that we've shown here, the class blueback has a specific background color. If other CSS characteristics were part of this class blueback, these characteristics would also be part of the div labeled d1, as a result of assigning the class blueback to the variable dd1 in JavaScript. The next line similarly assigns the class yellowback to the variable dd2, which is storing the HTML element with ID d2. Again, in action, using the onClick event handler to call the JavaScript function changeColor assigns these CSS classes to the chosen HTML elements, and we see the background change. It's also possible to change other attributes of HTML elements, like the text associated with an element. This function changeText uses a very similar approach to what we just saw with changeColor. The first two lines create variables to store HTML elements, and these are exactly the same lines as we just saw with changeColor. Just as before, to access attributes of an HTML element, you'll use the dot syntax and the name of an attribute or field that will be used in JavaScript. The attribute shown here, .innerHTML, accesses the HTML content within the element. In this case, that's everything inside the div, which is text. This line of code, dd1.innerHTML gets bonjour, changes the text of the HTML element accessed by the variable dd1. That's the same HTML element whose ID is d1, which used to show the word hello before the code executed, and will now show bonjour after the code runs. It's worth pointing out that while dd1 is an HTML element, a div specifically in this case, in general it's just an object, like a CSS style or simple image are objects. You can always use documentation to find out what methods operate on different objects. In Actions, here you can see what happens when you click on the Change Text button. An on-clicked event handler calls changeText the JavaScript function we just saw, which accesses the HTML inside the divs and sets it to new text, bonjour and sayonara. We'll provide some resources to show how you access other attributes using JavaScript as you practice making web pages and changing them interactively. Bonjour and sayonara. Hi, let's see how to create a web page and write code that will move us closer to the green screen page. Rather than using div elements, we'll use a new HTML element named canvas. The canvas HTML element is used to store images in the Duke Learn to Program, or DLTP environment that you've seen before. A canvas has a different functionality than a div. As you'll see, it's possible to draw shapes, lines, and more. We'll only explore basic functionality of this HTML element. You'll see how it's accessed via JavaScript, and you'll be able to do more if you explore additional resources. Previously, you have seen the div element used to specify a section of a web page, so that the background color or other attributes can be changed programmatically by referring to the element ID, in this case D1. On this page, the Make Lime button changes the background color to lime, and the Make Yellow button changes the background color to yellow. Let's try using canvas element instead of div. You'll see that we have to make a few changes to the CSS and to the HTML panels. When we use canvas, the hello text disappeared. It turns out that special methods are necessary to write text in a canvas. But as you can see here with the canvas, the background color changes work the same as they did with HTML div elements. We'll see more closely how to program with a canvas as we explore this functionality in more detail. Let's talk about how a canvas is used. It's used specifically to draw graphics. Usually, it's used with JavaScript. You should think of it like a container for graphics, where the container needs to be filled in, which you do by writing a script. There are several methods that you use to create these graphic tasks, such as drawing paths, boxes, circles, text, and adding images. We'll show a simple interactive page using a canvas element. We'll create a web page with 2 buttons using HTML, CSS, and JavaScript. Each button will change a different feature of the HTML canvas element. One will make the background lime, and the other will draw yellow squares and create text in the canvas, all with JavaScript. Let's program. Let's look at an example of using CodePen to combine HTML, CSS, and JavaScript to make an interactive web page using a canvas. As we saw in the recent lesson, I'm going to have a canvas that's going to make both color background changes and draw using the graphics element. I'm starting with a canvas. We see that we've got the canvas element here. Its ID is D1. And we have 2 buttons. One that says make lime, and it calls a doLime JavaScript function. One that says make yellow and calls a doYellow JavaScript function. The functionality that we have that we start with, which I've already coded, is make lime. We can come over here and just review a couple of concepts. I use the standard document.getElementById to grab the element whose ID is D1. As a reminder, that's this canvas. And then I make the background color lime. That's why the function is called doLime. In the make yellow function, which is the button that calls doYellow, I get the element by its ID and I make the background white. So right now making yellow actually turns it white, but I'm going to make it white in preparation for making some yellow rectangles. Let's also just review very quickly that there's some CSS for the canvas that styles it to have a specific width, a specific height, and a border. That's why when we start with the page blank, we see that the canvas is here with nothing in it, a little narrow border that's 1 pixel wide, as we can see here specified in the CSS, and these 2 buttons. So let's look at the doYellow JavaScript function and see how to make yellow rectangles appear by using the canvas. The first step is going to be that rather than drawing in the canvas, we're going to have to access the context of the canvas. That's a new concept for canvases, that the graphics are actually displayed in the canvas's context. The way we do that is create another variable. I'll call it CTX for context, and I'll get the context from the canvas, which is stored in variable dd1, and the name of my method is getContext. I'm actually going to take off my little bracelet because it's kind of jangly, so excuse me while I remove it and put it right there. It's kind of hitting the keyboard and it's annoying to me. Might be annoying to you. So I'm going to call getContext, and I have to specify that I'm getting the 2D context. In other examples, we might see something beyond 2-dimensional, but all the graphics I've ever done and that we'll ask you to do are the 2D graphics. Now that I have the context, I have to fill it with yellow squares. The first thing I'm going to do is do something similar to what I did by setting the background color. I'm going to set the fill style to yellow. That means anything I draw will be in yellow. Then I'm going to fill a rectangle. That's the name of the method there is fillRect, and I have to specify where it's going to be. I'm going to use this to see what happens. I'm going to actually test it. First I'm going to save it, and I'm going to review the code that I wrote and then test it. I got the graphic context. Then I set the fill style of that context to yellow. And then I created a filled-in rectangle, and I specified the coordinates of the upper left portion of that rectangle, which are at 10, 10, and the width and height of the rectangle, which are 40, 40. Let's see how that works. I made it lime. Making yellow doesn't do anything. So right now, I have to look because there's a bug in my code. Luckily, CodePen helps me find that bug. You can see that this is in yellow, whereas this is in blue. I didn't spell the name of the variable right. Context is CTX. So now I'll call make yellow, and I see up here a yellow rectangle, exactly as I'd expected. Just to see I understand the parameters, let's make this rectangle bigger. 60 by 60. I'm hitting save. Make yellow. That rectangle is definitely bigger. Just because I can, I'm going to make that rectangle 100 by 100. I want to make sure I understand that that makes the rectangle bigger. Sure enough, it's bigger. I can actually change where it's drawn by changing that 10 to a 50. Let's see what happens. The rectangle is lower on the page because these are the x and y coordinates. X goes along the width and y goes along the height, with the upper left corner 0, 0, as you learned in our Duke Learn to Program when we were talking about images. I'm going to set that back to 10, 10, 40, 40, and then I'm going to draw another rectangle. This rectangle is going to be near to the other one, almost adjacent to it. I'm going to make it at 60, 10, and also make it 40, 40. I'm going to not forget my semicolon. Let's see what happens when I make that yellow. I now have two rectangles. Notice if I make the background lime, that draws behind the rectangles because it's the background color. Making yellow changes it to white because, as we saw here, the background color was changed to white. Remember that when you write code, the method or function that you call executes from top to bottom. Make it white, get the context, make the context yellow, draw two rectangles. I've got one more thing to do with the graphics, and that is I want to create some text. I'm going to make the text in a different color. So I'm going to set the fill style to black, and then I'm going to draw some text. And I draw text by saying fill text. I specify the text I want to draw, which in this case is hello, and I specify where to draw it, which is 1080. Let's see how that works. I can't see hello anywhere. Once again, I've spelled the variable wrong. Apparently, do that often by mistyping. There's hello, very, very small, down there below the yellow rectangles. I can make the font different by setting the font style of the text just as I set the fill style. So I'll set the font to a bigger font, 30 pixels, and because I'm fond of Arial, I'll change the font to Arial. Notice, I now have hello in a bigger font. It's 30 pixels. Just to make sure, let's make it 50 pixels and see if that makes it bigger. That's definitely bigger. Unfortunately, it overwrites the rectangles, so I'm going to set it back to 30. I'm going to save it. I'm going to test all my buttons. Make lime, make yellow, make lime. I've got two yellow rectangles done by the context's fill rect methods. Notice I've set the style to yellow. If I had set the style to purple, for example, and spelled it correctly, when I call make yellow, it makes purple rectangles. That might be confusing, so I'll leave it back at yellow. You can explore more of the graphics context using the resources that we provide. Have fun writing code with canvases. I do.
In this lesson, you're going to learn about new HTML input types and events. You've already seen the button input type with the on-click event, and now you will learn how to use additional input types and events to make your web pages even more interactive. As you have seen, the HTML input tag is used to create an HTML element like a button that gets input from the user and processes that input with JavaScript code. You've already used a button to get input from the user, but you can also create web pages that ask for text input. You've likely seen web pages in which you enter a name or a password or a URL. You can present the user with a color picker tool, such as this one, or a range, which gets information from the slider, both of which you'll see in this lesson. There are many other options you can find in the documentation for the HTML input element. In the case of a button, the input is the user clicking on the button, the on-click event. But as you'll see here, there are other events that you can connect to a button or another type of input. For example, here is an article on the Duke Today website. The content highlights when the mouse rolls over it. The on-mouse enter and on-mouse leave events are used to have the browser execute any function you connect when the mouse enters or leaves an object. Changes to a field or input can also be useful events. Here is an example of a search function executing on the Duke Today website. as user input is typed in to look for articles about Duke's Kunshan University. A color picker, or color chooser, allows the user to choose colors as part of interacting with the web page. The color can be specified by name, by using sliders, or selecting RGB values, or more. Note that color was introduced with HTML5, and new input types that are not supported by older web browsers will behave simply as input text types. Let's look more closely at how a color picker or chooser works. Here is the input tag, which you have seen before. The type for a color chooser is color, and here we have specified a default value of dark blue. This color picker element has an ID so that we can refer to it in our JavaScript code and represent its input with a variable. Many inputs require connecting events other than mouse clicks or moves. A color chooser uses an onChange event. This may be connected to a mouse, but isn't based on clicks, just when the color chooser's value changes. This event is connected to JavaScript through the onChange event handler. Now let's look at the function doColor. This function can be named anything, but must match the name you specified in the HTML input element. Accessing the color picker value in the JavaScript code uses functions and concepts that you may recognize. First, the canvas element is stored in variable dd1, as you have seen before. Then, the color picker element is stored in the color input variable, using the same technique to find the element in the document. As before, you can choose any name you want for your variable names, but the IDs given in the strings must match those IDs given in the HTML elements. The value of the color chooser is accessed using the .value attribute or field of the color chooser HTML element stored in the variable color input. Next, we use the .style attribute to set the background color of the canvas to whatever color the color picker is currently set to. The basics are the same here as they are with a button input. Connect JavaScript code to an event using the HTML input element and the appropriate event handler. Let's see the color picker in action. The Make Line button still works. Now, clicking or moving the pressed mouse button over the color options will change the color shown in the color chooser dialog. Pressing down on the mouse will change the active color in the color chooser and generate an onChange event. This event is also generated if you keep the mouse pressed down and move it over the colored pencils. When the mouse is down, a color change event can be generated. What happens if we change the event we are responding to from onChange to onClick? Now, clicking on the color picker with its default of dark blue changes the canvas background, whereas it did not for the onChange event, because the element had not been changed. In this case, changing the color chooser does not change the canvas color until we click on the color picker element itself. This is the difference between the onChange and onClick events for an HTML input element. Let's look at one more type of HTML input and the events it uses, the range or slider input. Here, the slider is horizontal and has a label of text indicating its purpose is to make a square using a slider. As the slider is moved, a square is drawn with side lengths determined by the value of the slider. The square can be made larger or smaller as the user drags the slider right or left. The HTML to create this slider has an input type of range with 3 parameters you specify when creating the HTML element. The minimum value of the range, here that's 10, the maximum value of the range, here that's 100, and the current value when the slider is first rendered in a web page. Here that's 10, which happens to be the minimum value, so the slider will be first rendered all the way to the left. The ID of the input element is important for accessing its value to use in the function doSquare. When you click and drag the slider, you generate an onInput event that you can use to connect the web page with your JavaScript. Let's look more closely at the function doSquare now. This is the function doSquare, which draws a square with side length given by the range input. As before, we store a reference to the canvas in a variable. Then we use the ID for the slider element to create a variable size input representing the slider. We get the value of the slider element and store it in the variable size. As you have seen before, we need to get the context of the canvas in order to draw in it. Finally, we use the size input from the slider to draw a yellow rectangle starting at the coordinates 10, 10, whose side lengths are determined by the size variable. Let's see what this code does. The square can be made larger with the slider, but it doesn't seem to get smaller. This is because each time the onInput event handler calls the doSquare function, it draws another square, one on top of the other. But the old ones are not cleared. Luckily, there is an attribute for the context that can clear a previous drawing. .clearRect will clear a rectangle given 4 parameters, 2 for the top left coordinates of the rectangle, and then its width and height. For simplicity here, we will clear the entire canvas each time doSquare is called. That's better. Now the square resizes with the user input from the slider. Now you know how to use new types of input, the color chooser and the slider, and you know new types of events to use with them, onChange and onInput. Have fun as you continue to make interactive web pages. In this lesson, we'll go over a few concepts that will allow you to upload image files and display them in an HTML canvas. We'll need some new programming concepts and JavaScript tools as we move towards creating an interactive web page for the green screen algorithm. You'll be able to create more web pages using these new concepts and tools as we move from a very simple page towards the more complex and creative green screen and mini project pages. We'll start with a prototype, a web page that's a model of what we want, but is simpler to understand. We'll need a new type of input element to upload our image files, but we'll start with a simple idea in this first prototype so we can concentrate on the idea rather than the details of the new HTML element. A simpler input type would be text input, which will display a text box like the one you see here that allows the user to type text. We'll test and understand the concepts with the prototype, reviewing the JavaScript for processing this and any other HTML element. Then we'll change the input type to file, and we'll introduce concepts needed to upload an image file and display it in an HTML canvas. Let's look at this prototype to understand the web page and the JavaScript. The HTML text input element allows the user to enter any text. As you can see in this simple page, the user has entered lion.jpg and is about to click the button. Here we'll use a button to process an event. It's possible to process text when the user presses the Enter key, but we'll use a button since they're familiar. As usual, when the user clicks the button to generate an event, we'll write JavaScript to handle that event. Here's that using the onClick event handler. Here's the JavaScript to process what the user entered. We'll use familiar JavaScript to access the value of the text input element and display that result in an alert box. So when the user clicks Upload, the alert box pops up. Remember, this is an example of text input. The input element doesn't care if we enter a file name. We could have entered any text. When we change to the input type to file, we will be guaranteed that the value we get represents an actual file. Though, as we'll see soon, we will need to do some work to ensure that that file is an image. Let's look at some new concepts. We'll use the last pen as a model and extend that prototype to a web page that allows the user to choose an image file, upload it, and display it in the web page. We'll replace the two inputs of type text and button with a single input of type file. We'll create an image from the file chosen by the user and uploaded. This will be a simple image from the Duke Learn to Program library that you've worked with before. You'll create the web page by extending the functionality we saw in the prototype. Starting with something familiar helps with understanding the new concepts, in this case, the file input and a library of JavaScript code. Starting with something familiar also helps with debugging, since we start with a working web page and working JavaScript. Let's look at how HTML and JavaScript combine to allow you to upload and display an image. Here's the HTML for specifying an input element that allows the user to choose a file and upload it to a website. You'll use file rather than button or color as the type of the input. You'll make sure the user only uploads one file, not several, by using the multiple attribute and making it false, signifying that multiple files cannot be chosen. You'll only allow the user to select image files, not text files and not audio files, for example. You do this by specifying a value for the accept attribute. The value is image/star as shown here. Star meaning all image types, not just JPEGs, for example. As usual, you will provide an input to make it possible to find this element within your JavaScript code. You'll use onChange for the event handler. This event is triggered when the user chooses a file by clicking the button displayed on the input element. Note, you do not need to add the button element. It's included with the file input type. Here is what the user sees when she clicks on Choose Files. A file selector appears. This one only allows image files. Yours may look different since different browsers handle this restriction differently. And once the image lion.jpg is selected, the file input is changed to contain the file. This triggers the onChange event handler. So let's see what the upload function should look like in order to achieve our goal of displaying the image in our canvas element. The upload function gets the canvas element and the file input element, each by its ID specified in the HTML. Then you'll create a simple image variable from the HTML file input itself. Wait! Simple image is not a standard JavaScript. It's a library of JavaScript code created for this course and hosted at DukeLearnToProgram.com. The code is automatically included when you use our custom JavaScript environment. But for web pages you create, you need to specify the source of this library. Let's see where to do that in CodePen. In your editing view for the CodePen page, the source for JavaScript goes in the HTML panel, not the JavaScript panel, enclosed in open and closed script tags with the attribute src for source. You can see the last part of the URL is simpleimage.js because that is the library we want the page to be able to use. Outside of CodePen, you would also use the script tag. Here is the code that includes the simpleimage.js library from our Duke Learn to Program site. Now that we know how to tell a web page where to find our JavaScript code, let's finish putting an image in the canvas. We have just created a new simple image from the file input HTML element. The last step is to use the drawTo method, a method included in the simple image library. We will call image.drawTo and use the canvas element as the parameter to indicate the simple image should be drawn on a specific canvas of our choosing. As always, you should try not to memorize all of these methods. You can consult the documentation at any time, like this documentation from DukeLearnToProgram.com. Now let's see the upload function in action. As you can see, when lion.jpg is selected as file input, the file selector is changed and the onChange event handler is triggered. For this event, that is the upload function, which displays the selected image on a web page by drawing it to an HTML canvas. Now you can create web pages that allow users to upload images too.
Hi. Let's look at changing a simple image programmatically, using the same concepts you used in the previous module. In the foundational programming lessons, you modified pixels in an image. For example, you changed different parts of an image to create stripes, so that part of the image was red, part was blue, and more. You also saw how to modify all pixels of an image as part of creating a new image that was a green screen composite of two images. We'll use these same concepts of modifying pixels to create interactive web pages that use this simple image library. Let's look at creating a grayscale version of an image. Grayscale is a common filter. We'll start with a CodePen web page that already has functionality to upload an image. We'll fork it, and we'll add a button to create the grayscale web page that takes an image, like the waterfall on the left, and converts it into a grayscale version as shown on the right. Extending a working web page continues what we did earlier with the prototype web page before we introduced the HTML file input type. The button that we create we'll call a JavaScript function named makeGray, using the standard onClick event handler. We'll need to access the uploaded image in this function makeGray. This will require a new programming concept, global variables. A global variable can be accessed in all functions because it's defined outside of any of these. That's what makes it global. We'll see that a global variable for an uploaded image can be accessed in the function upload and also in the function makeGray. The global variable is set or assigned a value in upload and then accessed or modified in makeGray to create the grayscale version of the image. The first 4 steps in writing a program are to devise an algorithm. We know that what makes a color a shade of gray is that each of the red, green, and blue values is equal to the others. And we'd like for our grayscale image to retain variations in brightness of the original image, so it won't just be black and white. One way to do this is to average the RGB values and to set the new RGB values to this average. Let's look at the first step, working an example by hand with some sample pixels. To do any math on this green pixel, we need to know the RGB values. For green, that's 0 red, 255 green, and 0 blue. Averaging these values means performing the operation 0 plus 255 plus 0, all divided by 3, which is 85. That means the new grayscale pixel will have R and G and B values each of 85. Which looks like this. Try this for magenta. We can see the RGB values. Did you get 170, a gray that looks like this? If you'd like more practice by hand, try the grayscale algorithm on maroon, sky blue, and orange with these RGB values. Did you get these answers? Now we've done steps 1 and 2, working an example by hand. You wrote down what you did. We can now generalize these steps. Start with the image we want, and then for each pixel in the image, obtain the R and G and B values, calculate the average value, and then set each of the RGB values to this average. Finally, display the final image. Using the Duke Learn to Program environment, you wrote code to process all pixels in an image to change their color. We'll use that same idea of looping over pixels to create a grayscale version of an image in our interactive web page. Let's look at translating this algorithm into code. Recall that we're adding a button, makeGrayscale, whose onClick event handler is the function makeGray. Let's look closely at this function makeGray. Here's the JavaScript source code for the makeGray function. We'll look at each line and see how the code works to convert an image to grayscale. Let's assume that the first step of the algorithm is already complete. The variable image was previously defined. To do steps 2 of the algorithm, we loop over all pixels in an image by creating a variable to represent each pixel, and then using the image method .values to access all the pixels. We calculate the average of the RGB values by accessing each of them, adding them together, and calculating the average. Then we set the pixel's red value to the average. then the green, and then the blue to the same average. Finally, to perform the third step of the algorithm, to display the grayscale image, we access the HTML canvas element by calling document.getElementById with the ID of the canvas. Here that's CAN or CAN. We use this canvas by passing it to the image's drawTo method, so the image draws itself in the canvas and we see it on the web page. We do need to address the first step of the algorithm. Let's take a look. We need to start with the image we want. Where is it? In our version of the web page that only uploaded a file, changing the file selector by clicking on it called the function upload, where we created an image by calling new simple image. But now we need this image in the function makeGray. How does makeGray access a variable initialized in another function? Let's solve this problem. Since upload is where the variable image is defined with the var, VAR keyword, that means a function like makeGray cannot see variables defined inside the function upload. And image.values will not work. We need global variables for this, so that many functions can access the same variable. We can still use the variable image in the upload function, but without the word var, the keyword var. A global variable can be accessed in all functions. Let's see how to use global variables in code. A global variable is defined outside of all the functions, using the same JavaScript keyword var, to create the variable. The global variable can be used in each function without using var. Remember that using var creates a new variable. Here, the variable image is assigned the value of calling new simple image. It's assigned it inside the function upload. Here, the variable image is accessed in the function makeGray to loop over all pixels in the image. Note that the variable pixel is defined with var, but the variable image is not. And here, image is used again, so that it can be displayed in the canvas by calling the image.drawTo method. Be careful when using global variables. If you had defined the variable image using var inside the function upload, you wouldn't be assigning to the global variable, but to one defined for the first time in upload. This is a hard bug to find sometimes. It's possible to have more than one global variable. For example, suppose we want to display the original image without the grayscale alteration, without uploading the image again. We could create a new image in function makeGray, rather than modifying the uploaded image. We could store both the regular image and the grayscale version in two different global variables. You'll have the opportunity to try out this alternative, where you don't alter the original image. Try to minimize the use of global variables. Relying on too many can make it hard to understand the code you're developing and how the functions interact with each other. Happy coding! Let's look at how to use concepts, tools, and programming to create an interactive green screen page. We'll use HTML elements like canvas and inputs for files and buttons to create an interactive green screen page like this one. You can see two images have been uploaded. I'm about to press the Create Composite button. That will combine the two uploaded images into one using green screen code you've seen in the Duke Learn to Program environment. There are several steps you'll need to take to use the code you developed in the Duke Learn to Program environment and make it work in a web page. You'll need to use HTML input elements to allow users to select files. Those input elements need event handlers to connect the events to JavaScript code. You'll need to create functions to load the images, and global variables so that all functions can use these images. To make the green screen appear, you'll use the drawTo method instead of print. Finally, we'll show you how to protect your code with checks to make sure that it works without error. Let's look at the components of this interactive web page. We'll look at the HTML elements first, and then we'll connect these to JavaScript. You can see here that there are two standard canvas elements. Each one has a border that's part of the CSS for the canvas. There's one canvas where the foreground image will be displayed, and another canvas for the background image. You'll also see 4 input elements. 2 are file inputs for the images, and 2 are buttons that change what you see in the canvases. The file inputs are labeled with their purpose on the web page. Upload a foreground image and a background image. 2 buttons are used, one to create the green screen composite and one to clear the canvases. Let's look in detail at the HTML file elements. We have 2 file inputs, one to upload the foreground image and one for the background image. Here's the HTML for these labeled images. We'll review the HTML elements and the concept that you've seen before. We create a file input to allow the user to upload and display an image file. Here's the foreground file input, and there's also a file input button for the background image. These file input buttons have unique IDs. This will allow them to be identified as needed in the JavaScript code that interacts with the web page. We see FG file for the foreground input and BG file for the background input. We connect these inputs to corresponding JavaScript to load and display the image in the canvas. We use the onChange event handler and call a JavaScript function. Here we're calling load foreground image. And here the event handler calls a JavaScript function named load background image. Let's look at the JavaScript code that's called when the user uploads an image. Uploading and displaying an image use concepts we've seen before. Here's the JavaScript function to load the foreground image. The background image function's very similar, so we'll just look at this one. We'll see that there's a global variable used for each image. The foreground image is referenced by the global variable FGImage. Here, you see that FGImage is initialized to null. Initializing global variables is a good idea. Using null will allow us to determine if an image has been loaded. When the user clicks the Create Composite button, for example. Null is a special value used in JavaScript and other languages to represent nothing. You'll see this idea again later and with other programming languages. Here, we see that the code that accesses FGImage. Notice it doesn't use the word var because the variable FGImage is global. The variable is assigned a new simple image element created from the file input element. Here, we see FGElement used again to draw to the canvas element that will be displayed on the web page. We will also use many local variables, like var img file. It references the file input for the foreground image. We use that HTML element because it's passed as a parameter when we create the simple image. Using local variables with the word var is a really good idea. Here, the local variable represents the canvas where the foreground image will be displayed. When a value is accessed in multiple functions, making it global is required. Otherwise, make variables local to avoid losing track when you have hundreds of variables, which might happen in the mini project. Let's look at the JavaScript code to create the green screen composite. We're going to look at the steps to create the green screen composite. We'll need some basic ideas from image processing that you've seen in the Duke Learn to Program environment. We've adapted these for use in a web page when the user uploads an image and then processes the image. For example, we need to check that the user has uploaded 2 images before clicking the Create Composite button. We accomplish this by checking to be sure that the foreground image is ready to go. If the global variable FGImage is null, the value it's initialized to when it was made global, then the user hasn't clicked the Upload Foreground Image button we just saw, because that JavaScript creates a non-null version for FGImage. It's also possible that the user has uploaded the image, but the image hasn't been completely constructed. Large images take time to create. The method .complete allows us to determine if the image is completely loaded. Here it says not complete. That's the bang or exclamation point. And if it's not ready because either it's null or it hasn't finished loading, we'll need to let the user know. We do this by displaying an alert indicating the code won't work. We check both the foreground image and we check the background image before creating the green screen composite. Now let's look more closely at the code to create the composite. Here's the JavaScript code adapted from the Duke Learn to Program or DLTP environment to create a green screen composite. The first step is to create a new image with the appropriate width and height. It will be the composite of the foreground and background image. The new image is initially all black, so we need to set each pixel by looping over all the pixels of the foreground image and copying either a foreground pixel or a background pixel, depending on how green the pixel we're looping over is. Here, we see that if the pixel's green value is greater than some threshold, we use the background pixel in the new image we created. And if it's not greater than the threshold, we use the other pixel. We'll also need JavaScript to display the new image in a canvas. Notice that the threshold variable, green threshold, must be global because it's not defined here with the word var. Let's look at the final steps. We'll need to display or draw the new composite image to create a canvas element with the image in it. We'll use the .drawTo method before making sure that the image appears. We know it will because we've checked to make sure it's loaded. And we'll clear the canvas elements before drawing so that we show only one image, the green screen composite. Let's take a look. Your working green screen page allows the user to interact by uploading images, one for the foreground and one for the background. We have to wait for those images to load and be displayed. Then we'll click the Create Composite and watch the green screen be created. We can see that the button stays clicked. It takes some time to create this composite. Then we see it riding dinosaurs. We can also clear them. There are no dinosaurs. Where did they go? We know that combining two people and dinosaurs can be lots of fun. You will also get to have lots of fun when you use the green screen program to create your own green screen composites. Have fun with programming. Hi, I'm here to talk about this exciting mini project that we have planned where you can combine all the knowledge and practice you have in using HTML, CSS, the skills you learned in the Duke Learn to Program environment, and creating an interactive web page to make a simple website that allows you to filter different images. Some of you may have a smartphone. You may have seen apps like Snapchat or Instagram where you can upload images and create filters that make them look different. We've already seen that in some of our previous videos, and now we're going to give you an opportunity to combine these skills and practices you have by making a website on CodePen from scratch. And when you make that website, you're going to allow the user to upload an image and then to filter it different ways. Let me run through a simple example of how that would work. Here I have what could be your final version, although we're going to ask you to create your own CSS so that it won't be styled as mine is in this unexciting wheat color. If I choose a file to upload by clicking my Choose File button, then navigating to, say, the brown horse image, now I see my brown horse. And if I click red, you can see the button stays clicked. Now the horse is red. I can reset the previous image, and then I'll see what I uploaded before, and now I'll make that image grayscale. This is what we hope that you'll be able to do as a basic mini project. Create a website in CodePen by creating the HTML and the JavaScript that allows the user to choose a file, upload the image, and it can be as exciting as the entire universe, and then make two filters. One that turns that image red, and another that turns the image into a grayscale version of what you started with. You can also reset the image back to its original version. That's what we'd like you to do for the basic mini project website. And of course, you can use different features of CSS to style the web page as you'd like. As a challenge, what we'd like you to do is to consider adding some more filters. Let me show you what the final web page looks like. On one hand, it looks similar, but I have different filters. I have a rainbow filter, where if I choose an image to upload, what I'll do with the small lion and the rainbow filter is to create a rainbow background. You might not be able to get the lion to shine through completely, and you'll have to do some research to find out what the colors of red, orange, yellow, green, blue, indigo, and violet are, the RGB values, so that instead of just red, you'll actually create stripes that way. We also like you to use a blur image. You can see here that I've blurred the lion using some techniques that we've discussed in the Duke Learn to Program environment. Finally, you might notice that as I click these filters, the dimensions of the image that I uploaded are displayed here, 250 by 188. If I upload a new image, something larger perhaps, like the brown horse, we'll see that when I click red, that image changes. And when the dimensions change. Creating the dimensions and adding them to the web page is another challenge activity we hope you'll do. These images could be lots of fun, and rather than just limit yourself to 4, you can make even more. I think it's going to be pretty exciting, and I'm looking forward to seeing what you all do in this mini project.
Hi. In this lesson, you're going to learn how to use functions to implement what is called steganography, hiding data in an image or other digital artifact like an audio file, a software program, or any file of zeros and ones. Because steganography is a bit larger of a task than previous problems you have solved, it's a great idea to break the code down into functions. As you progress through this lesson, you'll see some examples where pieces of code are abstracted out into separate functions to simplify the entire solution and to avoid repetition of code. The idea behind steganography is to take an image, like this image of sprinter Usain Bolt, and hide data, like another image, inside it, altering the numerical values of the pixels of Usain Bolt to encode the hidden image. The key to steganography is to hide the data in such a way that nobody can easily tell you have altered the original image. This image on the right is the result of hiding a secret message in the first image. Can you tell that it has been altered? If you look really closely, you can see some differences in the shading of the background. However, if you were to just look at this second image by itself, there is nothing suspicious. It just looks like a picture of Usain Bolt. This idea has been around for a long time, predating computers. Sending an undetected message has been important throughout history. One important modern use is to avoid censorship imposed by oppressive governments. You can hide any digital information in an image. You could, for example, hide a text or HTML file in an image. However, that would take a bit more math and a deeper understanding of how everything is a number. To keep things simple at first, you'll work with hiding an image in another image of the same size. When you are finished with this lesson, you'll be able to find hidden meaning in the universe. That is, we're going to walk you through not only the concepts, but also the code to do steganographic hiding. Then you will write the code to extract the hidden message from an image. For example, you could take this picture of a galaxy and extract the message that we hid inside of it. Okay, so how do you actually do this? You already know that pixels have red, green, and blue components which numerically represent the color. Is there a big difference between a red value of 240 and a red value of 255? They are numerically different, but if you look at them, the two of them are pretty similar. The fact that you can't easily tell the difference when you change the numerical value slightly is the key to hiding data in an image. You can store the hidden data in the least significant digits of the color value and not see much change in the resulting color. The least significant digits are like the ones and tens places in a 3-digit number. So you could hide a 15 in 240 by changing 240 to 255. To do this, you're going to need a bit of math. Don't worry, it's just multiplication, division, and addition. You just have to put them together the right way. To understand how to do this math, we're going to start with decimal, the base 10 number system you use every day. We'll explain the concepts in base 10, then learn about binary, the base 2 number system that the computer uses to store numbers. All the principles will be the same in base 2 as they are in base 10. You will just need to use powers of 2 instead of powers of 10. To see this idea in the familiar base 10, suppose that the values for the red, green, and blue went from 0 to 9999 instead of 0 to 255. This gives each component of the color 4 decimal digits. Now suppose you want to hide this red pixel with the RGB values shown. Red equals 8274, green equals 0, and blue equals 1098. In this blue pixel with RGB values of red equals 3568, green equals 5686, and blue equals 7450. We'll put the result here on the right. For the red, you want to take the most significant 2 digits of the pixel you want to hide the data in, which is the blue pixel, and use them as the most significant 2 digits of the result. Then you want to take the most significant 2 digits of the pixel you want to hide, the red pixel, and use them as the least significant 2 digits of the result. Notice that 3582 is pretty similar to 3568. It will look almost the same, but you've changed it slightly so that it stores the secret information in its least significant digits. Now you do the same thing for green, taking the 2 most significant digits from this blue pixel and combining them with the most significant 2 digits from this red pixel. Again, 5600 is pretty similar to 5686. Now you do the same thing for the blue component, combining the most significant digits from the 2 pixels blue components. The resulting number, 7410, is again quite similar to the original 7450. If you look at the resulting color of this pixel, it's pretty hard to tell the difference between it and the original blue pixel. But as you'll see, we've hidden a red pixel inside it. Now that the information is hidden, how would you extract the secret? You know that you want the least significant 2 digits of this pixel's red to be the most significant 2 digits of the hidden and soon to be extracted pixel's red. So we want 82 to be the most significant digits of the R, or red value. But what should the least significant digits be? It doesn't really matter too much, so we'll just pick 0. Then you do the same thing for green and the same thing for blue. If you look at the resulting color, it is this shade of red. That shade of red is pretty close to the original color that we wanted to hide. Even though you don't get the exact color back out, the extracted image will look pretty similar. So now you know the big idea. Steganography is hiding data in other data. In particular, you're going to do this with hiding one image in another. Now you understand the basic math that is involved in it, taking digits from each number and combining them. However, to implement this in code, you're going to need to learn a little bit about binary, the base 2 number system the computer uses, which is why the color values go from 0 to 255 instead of the 0 to 9999 that we just worked with.
Now that you have the basic idea of steganography, it's time to learn a bit about binary, so you can do the math on the numeric values of pixels. Let's start with a refresher on base 10 numbers, the normal decimal system you use every day. In a base 10 number, the digits are in the ones place, the tens place, the hundreds place, and so on. This means that a number like 8,237 is 7 times 1 plus 3 times 10 plus 2 times 100 plus 8 times 1,000. The same principles apply in binary, but the places are powers of 2 instead of powers of 10. Computers do this because they fundamentally work with electric circuits and transistors, which are easiest to implement with 2 voltage levels. So computers work naturally in a number system where you have only 2 values, ones and zeros. So the binary number 10111 is 1 times 1 plus 1 times 2 plus 1 times 4 plus 0 times 8 plus 1 times 16, which, if you wrote in decimal, would be 23. The red, green, and blue components of pixels range from 0 to 255 because they are stored with 8 binary digits, called bits. Note that the B in bit comes from binary, and the IT in bit comes from digit. With 8 digits, or 8 bits, a number can range from 0000, 0000, which is the decimal number 0, to 1111, 1111, which is decimal 255. These 8 bits are in the ones place, the twos place, and so on up through the 128th place. If you were to add up all these place values, you would get 255. Now that you know that each color is an 8-bit binary number, let's revisit the steganography problem. You want to hide the 8-bit number on the left, 1011, 0010, in the number on the right, 0111, 0101. As before, you'll hide the most significant digits. In this case, you use the 4 digits from each number, since that's half of the total digits. The resulting number would be this 8-bit binary number, where we've colored the bits based on which of the 2 original numbers they came from. The most significant bits from the number you want to hide, shown in blue, are now hidden as the least significant bits of the color that will be displayed. That's how you do it conceptually. But how do you pull these numbers apart and then put them back together using mathematical operations that you can write down in code? Let's again revisit the problem in the more familiar context of decimal numbers. Working similar problems in more familiar contexts can be a great strategy in general, whenever you're approaching problems that have unfamiliar concepts. The first question we might ask is, how do you extract or get 82, the blue digits, out of 8,274, the number on the left where the 82 is underlined in blue? You could take 8274 and divide by 100. That would give you 82.74, and then throw away the 0.74. The mathematical operation called taking the floor of a number, which means rounding it down to the whole number less than or equal to it. In JavaScript, you would do this with math.floor 8274 divided by 100, and that would give you 82. The same principle works to get the most significant 2 digits of 3,568. Math.floor of 3568 divided by 100 is 35. In fact, you can get rid of the least significant digits of any base 10 number by dividing by the appropriate power of 10 and discarding the fractional part. Now that you have 82 and 35, you want to put them together to get 3,582, which you can do simply by multiplying 35 by 100 and adding 82. In fact, this strategy works to combine any 2-digit numbers into a 4-digit number. If you wanted to combine numbers with more or fewer digits, you would multiply by a different power of 10. Now, let's go back to the numbers represented in binary. You can apply the same principle, but now you'll need to use powers of 2 instead of powers of 10. And since we want to work with 4 digits at a time, we'll use 2 to the 4th, which is 16. So if you took math.floor of 10110010 divided by 16, you would get 1011. Note that there's nothing really special about binary math. Binary numbers are still just numbers. In fact, this really is 178 divided by 16, which is equal to 11. We just wrote the numbers down in binary rather than decimal. Similarly, to get the most significant 4 bits of the other number, you can divide by 16 and take math.floor of the result. In this case, you're taking 117, dividing by 16 to get 7. Now, you can combine the 2 different 4-bit numbers into one 8-bit number with the same principle we saw before with base 10. But this time, instead of multiplying by 100, you multiply by 16 and then add. That's the math required to hide one image in another. But what about the math to extract the hidden image? How do you get the least significant 4 digits out of the number on the right, shown in blue, to make them into the most significant 4 digits of the number on the left? Let's again go back to the more familiar base 10 scenario. When you take 3582 and divide by 100, you get 35 with a remainder of 82. That 82, the remainder when you divide, is exactly what you want. So how do you ask JavaScript to give you the remainder that's left over when you use division? You use the % operator shown here. 3582 %100 is 82. The % operator is called mod, short for modulus, the formal mathematical name for the remainder when you divide. So we'd actually read this statement as 3582 mod 100 is 82. Once you have these two digits, you can just multiply by 100 to get the number you want, making them the two most significant digits of the resulting four-digit number. The same principle will work for binary digits, but again, you use powers of 2 instead of powers of 10. Since you want 4 digits, you would use 2 to the 4th, which is 16, instead of 100. Taking a number mod 16 gives you the 4 least significant or rightmost bits, the binary digits, in this case 1011. If you take that number and multiply by 16, you end up with these bits as the 4 most significant bits of an 8-bit number. You see that the leftmost or most significant bits are now 1011. That's exactly the math you need to extract a hidden image. So now you've seen how numbers are represented in binary and how you can extract the digits you want from numbers in base 10 or in base 2 using either division or mod. You've seen how you can combine these digits back together in either base using multiplication and addition. And you've seen that you can use math.floor to discard the fractional parts after you've divided. We've summarized these ideas on this slide. Remember, think about numbers in base 10, but do the math in base 2 by using powers of 2 instead of powers of 10. Enjoy your programming.
Okay, now you know the big picture of steganography, as well as the basics of binary math. Now it is time to look into putting all of this together. Let's suppose you wanted to hide this top image, which has a secret message, inside of this bottom image, which is a picture of the galaxy. You have already seen how to take the 8-bit numbers which represent one of the color components, red, green, or blue, and hide the most significant bits of one in the other. You take the most significant bits from the image you want to show up and combine them with the most significant bits of the image you want to hide. You've already seen this math to make this work, but there is a bit more to this than just doing math on one pair of numbers. You need to do this math for each pixel. Iterating through each pixel in an image should be quite familiar by now. And you need to do that math for the red, green, and blue components. Since you need to do the same thing 3 times, you might think about pulling that computation out into a function, allowing you to call the function rather than repeating the code for that task. Speaking of functions, since this task is a bit more complex, you might find it useful to break it down into a couple functions. We're going to walk you through a couple functions that we broke our implementation down into for hiding. First, we made a function called chop to hide, which is going to take the image we want to show up in the end and produce one that looks quite similar. It is going to do the math on each color component of each pixel that keeps the most significant bits and zeroes out the least significant bits. The algorithm for this function would be to iterate over each pixel in the image and do this math to the red, green, and blue components. You want to divide by 16, take the math.floor of that result, then multiply by 16. You might want to extract this repetitive math out into its own separate function, then just call it in each place. The resulting image should look pretty much the same as the original, as we show here. If you were implementing, testing, and debugging this code, breaking it into small pieces like this would be helpful. You can check the result of this one piece and make sure it works before moving on. The second function you might write would operate on the image you want to hide. We call this shift because it will shift the most significant bits over into the least significant bit positions. That is, you would take a color value like 1011, 0010, and convert it into 000, 1011. The 1011 has been shifted from the most significant bits to the least significant bits. The algorithm for this would be to iterate over each pixel and set the red, green, and blue to the math.floor of the original value divided by 16. If you looked at the resulting image here, it would look plain black. That is actually a great thing since all of the information is in the least significant bits and the most significant bits are supposed to be all 0. Again, you could test this separately before you move on. The final function, called combine, takes two images and adds red to red, green to green, and blue to blue to produce the color values of the resulting image. It should look basically the same as the original image. Once you have the ideas for these three functions, your high-level algorithm to hide one image in another looks like this. You just call the functions that we discussed, and they do all the work. Having seen the algorithms for each of these functions, you could translate them into code. For example, here is the chop to hide function. You can see here where we decided to pull out the actual math into its own helper function and call it for each of the red, green, and blue components. The other functions to hide would be similar. As we discussed, you iterate over the pixels of the image and do the math we previously described. What about extraction? How do you get the hidden image back out? We're going to leave that to you. You've already seen the math required, so now you can use the 7 steps to develop an algorithm and translate it into code. Start out with step 1 and work on an image with 2 pixels. Write down numeric values for their red, green, and blue. Then extract the hidden 2-pixel image. Once you have done that, work through steps 2, 3, and 4 to develop your algorithm, then translate it into code, test it, and debug it. Happy coding! Okay, we've walked through some of the concepts, and we told you we would walk you through the code to hide one image in another. We've started here with the clearbits function, which we'd seen before in a previous video, which just takes the math.floor of the color value divided by 16 and multiplies it by 16 to clear out the lower bits. We've previously talked about the chop to hide function, and we've written down here the steps for the algorithm for that, and we're just going to turn those into code. So we need for var px of image.values, that's how you've seen to iterate over the pixels in an image before, and we want to clear the low bits of the red, so px.setRed to clear bits, this function we wrote to do the math for us, of px.getRed. So we want to take the current red value, call clear bits to zero out the lower bits, and then set the red to that new value. We can do the same thing for the green. And the blue. And then when we're finished, our image that we've been modifying is the answer to our whole function. That's what we want to give back to whoever called us. Now, I've got some placeholders for the other functions we're going to write here in a second. And at the bottom here, I've got this algorithm that we saw as our high-level algorithm where we combine chop to hide, shift, and combined. So at this point, these two functions don't do anything, so printing our overall answer is not going to do us much good. I'm going to comment these lines out, and instead, I'm just going to print start so we can make sure that that works pretty well before we do anything else. So if I run this code, I'm working with our picture of Usain Bolt. I get something that looks pretty similar as with the previous videos. You can notice that the background colors have changed just a little because I've been modifying these color values. Great, now let's go work on shift. So remember, this is where we're going to take those most significant bits and move them over into the least significant bit positions for the image we want to hide. So our algorithm is going to call for us to iterate over each pixel in the image. And what we want to do here is to shift over the red bits. So we want to px.setRed. And remember, we can do this by dividing by 16. px.getRed divided by 16, because 16 is 2 to the 4th power. That will move everything over 4 binary digits or bits. Now we want to px.setGreen to px.getGreen divided by 16. And similarly, px.setBlue to px.getBlue divided by 16. And again, we've written this little bit of code. We'd like to make sure that it works, or at least looks like it works, before we move on. We're not testing very thoroughly in this video. We would encourage you to do more extensive testing of your own code. So what if we now hide and we print out hide? Oops, we left off. If we go back up here, we got sort of a weird error message. Cannot read property get string of undefined. What does that mean? Well, something was undefined. That's generally a bad thing. If I go back and look at this, I forgot to return my answer. Oops. And now we get an image that's mostly black. If you remember from before, that's what we want. We've hidden all this information in the least significant bits. We can't really see it. Even though we just fixed one little compiler error, it was really good that we got that fixed before we had a big mess of code where it might have been harder to find that problem. Finally, we need this combine function. We want to make a new image. We're going to call it answer. It's going to be a new simple image of the same size. So we want show.getWidth and show.getHeight. These are show is one of the parameters to combine the image we want to show up, and hide is the other image which we want to hide. We're going to assume they're the same size right now. That's not very robust. You'll write some code to crop the images to be of the same size. Then you can work with any images. And for each pixel in answer.values, we want to get the x and y of that pixel. So var x equals px.getx. You should be pretty familiar with that by now. And var y equals px.gety. Again, a familiar thing. We want to get to the same pixel, show pixel we'll call it, from the show image dot get pixel with xy. And we want the same hide pixel, hide.getPixel, the same pixel from the hide image. And now we want to set px's red to the sum of show pixels red plus hide pixels red. Remember, that's going to combine the two together. One of them is going to have the most significant 4-bit set and the other 0. The other is going to have the least significant 4-bit set and the other 0. So when they get added together, we'll get a whole 8-bit number. And then we're going to do the same thing for green. And for blue. And after doing that for each pixel, our answer is going to be the image answer. So now I'm going to come down here. I'm going to uncomment these last two lines, get rid of the extra one I wrote. Now we get this image of Usain Bolt that looks like what we expected. Are we sure it's right? Not really. We'd want to investigate a little more. We could have just messed up and maybe returned our start image somewhere or something like that. We're not going to test terribly rigorously in this video, since that would take more time. We would leave that up to you. So with that, I leave you with one final important question. What would happen if we hid an image of a stegosaurus inside of another image? It would be stegosaurisonography.